So this is what we saw the other day. So let's just go through it in like 15 minutes very quickly. Specific heat and latent heat. If you remember, specific heat is how much energy you have to add to raise 1 kilogram of substance, the temperature by 1 degree, okay? Or the temperature of 1 kilogram of substance by 1 degree. The latent heat is how much energy it takes to evaporate 1 kilogram of substance. It is latent heat of vaporization. You could also think of a latent heat of condensation, which is the opposite. And instead of taking energy, it releases energy. And you can also think of the latent heat of fusion, right? So one comment was actually asked in the chat the other day in Zoom, and I didn't see it actually, which was whether the latent heat of vaporization was actually a function of pressure. It is a function of pressure. It's also a function of temperature. I gave you some numbers the other day, but it's true that it varies a little. What I cared about the numbers I gave you was actually just the power to give you an idea of how it compares to specific heat and maybe to other materials that you find in nature. But it's true that the constants of latent heat and specific heat are not such. They are not constant. They depend on temperature, they depend on pressure. That's also why we use the specific heat at constant pressure, usually in the formulas. And I said the other day, the specific heat that we will care about the most is specific heat of the air rather than the water, right? So how much energy it takes to warm up the air. For the latent heat, we care about the water, how much energy it takes to vaporize water or is released when we condense water, all right? Okay, so that was the specific heat and latent heat, right? And I said that if the specific heat, you multiply it times the temperature change, you get an idea of how much energy has been added to warm up. That is the sensible heat flux, really, okay? If you multiply times the specific heat, you multiply times the density also, and the change in temperature, because the density multiplication converts that specific heat into heat capacity, which is per volume, right? If you multiply that times the temperature change, then you get the sensible heat flux. If, on the other hand, what you have is a latent heat flux and you multiply it times the evaporation flux, then you get the latent heat flux, right? Lambda E. That, I think you can work it out yourself with the units because it'll become quite intuitive. Dalton's law. What do I care about the Dalton's law? I cared about the Dalton's law because I wanted to show you that two things. One is that the atmosphere is a mixture of gases, and that the atmospheric pressure is the sum of the partial pressures, meaning the sum of the pressures of the component gases, right? And the other thing I wanted to show you is that if you add water vapor to that, the air becomes lighter because the molar mass of water vapor molecules is very small, right? Very low. So in reality, when you think of moist air at equivalent temperature and so on, that air is actually lighter. And that is one of the reasons that air that is being moistened while the surface goes up. The other reason, which is more important, is that that air is also being warmed up by sensible heat. And that really makes it a lot lighter, right? So moistening and warming the air makes it lighter. Clausius Clapeyron law, that was that exponential curve that you saw in there, which implied that if you have air that is warmer, it takes more water vapor before it saturates. And that is disproportionately when it's warmer. So when you have warm air and you increase it by 1 degree, it takes much more water than if you have cold air and you increase it by 1 degree, right? And that was, as I said the other day, quite important. And it actually helped us understand some concepts such as the vapor pressure deficit, wet bulb temperature, dry bulb temperature, dew point, and so on. Hydrostatic law. This air right now is in hydrostatic equilibrium. It's not moving up or down, or at least not noticeably. That is because if you were to isolate a parcel here, like size of a football, if you wish, the weight of that would be equivalent to the pressure gradient that is pulling it up. Why does it have that pressure gradient? Because the pressure is higher when you go down and lower when you go up, right? So if it was for the pressure gradient, it would just go to lower pressures, but it also weighs. It has a mass and gravity. Then those two are in equilibrium. They are equal, and that's why it's not moving anywhere, the vertical. Okay? You can break that equilibrium. Essentially 2 ways you can do it, or 3 ways. One is to warm it and wet it, and then it becomes lighter, so the mass is lower, the pressure gradient is the same, so it tends to move up. You can also add, if that was moving in horizontal, but not in the vertical, if you add friction to it, then it starts changing the laminar path, and then you generate turbulence and it moves. And the other way would be through conversions. So you have air moving in here, and because you're increasing the pressure, then that air can go up. Okay. Okay. So that's the hydrostatic law. Law of ideal gases. This is really important to remember because it's crucial for any climate model, any numerical weather prediction model. You need to know how the pressure changes with temperature and volume and so on. So we said the law is just PV equals nRT, or if you wish, P equals density RT. If you throw the V to the other side, that's molar density actually. If it is easier to think in density than in volume because the air volume is a bit weird. So that is actually the law of ideal gases, and we said actually that it applies also to the components. So water vapor, you can also do that just for the pressure of water vapor, the E. So the water vapor pressure, okay? And the temperature of water vapor and so on. So another thing we saw was the first law of thermodynamics. That's just continuity law of energy. So conservation law of energy applied to thermodynamic systems. So in this case, the atmosphere, meaning that the energy cannot be created or destroyed. It has to be converted into something else. So if you have more energy coming than leaving, it's because you're either warming or evaporating moisture within that volume. That's essentially what it tells you. And you had 4 components in that equation, which was the input from outside or output. We said that if that was 0, the process is called adiabatic. And then you have 3 other components. That was the change in temperature, which was, as you imagine, densities, specific heat, a constant pressure and temperature change, so kind of like a sensible heat. Then you had the latent heat in there, which is just for the phase changes. So if you add energy and then that energy is used to vaporize, for instance. And the third component, which was a bit more specific of air, was this pressure component in there in that energy budget. That we said that when we actually make a parcel lighter and it moves up, then that is actually the work that the parcel is exerting on the surrounding when it's expanding. And as it is exerting that work that requires energy for the parcel cools down. So it actually lowers the internal energy to do it, unless it's releasing energy outside. For instance, I'm thinking of an adiabatic process in which the left side of that equation is 0. Maybe you don't have phase changes. And then we only have 2 components in the first law, which is the pressure and the internal temperature thing. So then, of course, they have to be balanced. So you use internal energy, you cool down, and then you exert that work to go to lower pressures. So that is what we call a dry adiabatic process, because you don't have energy from outside, so it's adiabatic, and it's dry because you don't have phase changes. So that is a dry adiabatic process. And the lapse rate that it yields, lapse rate just means change in temperature with height, is actually, we said the other day, about 10 degrees per 100 meters, right? So when you move the air dry adiabatically up without exchanges of heat from outside, so adiabatic, and without phase changes, so dry, then the cooling that is caused by going to lower pressures, the way I mentioned, is actually about 10 degrees per, so is it 10 degrees? No, yeah, 10 degrees per kilometer, 1 degree per 100 meters. So that is the lapse rate. That's the change in temperature with height. That's an adiabatic lapse rate. You could also have the wet adiabatic lapse rate. That is when you have condensation, and then that lapse rate will be less steep because the condensation is releasing energy. So as you move up, you lose less temperature with height because at the same time you have the energy release of condensation, right? Good. We said that it's better to think about temperature in terms of potential temperature, which is pressure corrected. Because if we were to have, for instance, a parcel of air here that is going to be moving up, and it will move up through the dry adiabatic substrate, you want to know whether the air that is now up there at 10 degrees and this parcel is at 20 degrees, once the parcel is there, it's going to be colder or warmer than those 10 degrees. So what you care about is the temperature that it'll have when it moves up through the dry adiabatic substrate. That is the potential temperature. Or if you want to view it the other way around, is the temperature that the air up there will have if you bring it down through the dry adiabatic substrate. And that way you can compare the temperature of the air here to the temperature of the air up there, which has a different pressure. So it's a pressure correction. And then we said that to be more precise, we could also talk about the virtual potential temperature, which doesn't only correct for the pressure, potential, it's the potential temperature, but it's also virtual, which means that you're also correcting for the effect of humidity in the density. Because if you were to have here air at 10 degrees, let's say, and here air at also 10 degrees, but the one here is actually wetter, it will be lighter and it will try to move up. So it's not just the temperature, not even the potential temperature, because they both have similar pressure, right? Because they are at similar heights, but actually the humidity can make a little change. So this one will have, the one that is below and has humidity has a slightly higher virtual potential temperature because of the humidity. So we have to compare them in equal terms to know whether there's going to be buoyancy, as we call that, positive or negative. So movements in a vertical due to the different density or the different weight of the air, right? Okay, virtual potential temperature. So what else did we see? We saw stability, which is what I just mentioned, whether the atmosphere is going to be prone to move vertically or not. If you have heavy air here and lighter on top, that's not going to tend to move. That's going to be a stratification. Maybe there is an inversion, sharp inversion in between the two, kind of like what you find in a lake, for instance, right? If what you have on the other hand is lighter on the bottom, then that'll tend to move up. And that diagnostic of whether the air is light is that virtual potential temperature. You have to compare the virtual potential temperature of the two. And then if one is higher and is below, they'll try to move up. If it is actually lower, they'll sink, and so on. So positive and negative buoyancy is what determines the stability of the atmosphere. You have stable atmosphere when it's all stratified, no vertical movements, there will be no clouds, nice weather. You can have unstable atmosphere when you have the air in the bottom trying to move up. It will be convection, clouds forming, bad weather typically, and so on, right? Convection and advection, that is just maybe going to confuse you, but convection is just the movement of a fluid, or the movement, if we're thinking of convection of a substance like a pollutant or CO2, or maybe water vapor or heat, the convection movement implies that those are moving with the medium that contains them. So it's not a diffusion, it's not a convection in which the medium is static like what happens inland, but it's actually moving together with the fluid. And that in the case of the atmosphere, the fluid is the air, fluids are gas and liquids, right? So the flow of that fluid causes the transfer of heat, moisture, pollutants. So they move together with the medium in which they are diluted. That's a convection process. Usually in meteorology, we talk about convection when we think about the vertical, and then advection when we think about the horizontal. And that's essentially the difference that you can think of. But in reality, and for this course, it doesn't matter too much, advection is not just the flow in the horizontal, but the convergence or divergence of a horizontal flow. And that has to do with the fact that if you have warm air here coming, but you're equally warm and you have an equally warm air leaving, then the budget is zero. Advection in reality is zero. It's not about how much it counts, but how much it counts compared to how much it leaves, convergence and divergence. But for the time being, you can think of advection as a horizontal flow, and convection is just everything, but usually we use it more in meteorology for vertical movements. So maybe a quick note on the energy transfers here. radiation, you know what it is, you're gonna get a lecture next week anyway. So that is a form of energy transfer that has nothing to do with what we're talking about in this lecture, not completely, but we'll go about that. That goes through light, as you know, lights, waves, and so on. Okay, that's one form of energy transfer. Another form of energy transfer you can think of is conduction. Conduction is, for instance, if you were to, like what happens in the soil, for instance, the heat, if you warm up the topsoil, the heat that goes down, it goes to conduction because the soil is not gonna move, it's not gonna essentially convect, right? So that is conduction. If you were to be cooking pasta, for instance, and you're stirring the pasta and you warm burn your hand, that's because the heat has passed through conduction across the fork, for instance, from the pan to your hand. What drives conduction? The gradient in temperature between the pan and your hand. Your hand is colder, your pan is warm, so there is a gradient in temperature, a distance between the two, which is the length of your fork. So that's gonna cause a flow that will be proportional to the conductance of that fork. If that fork is metal, which is conductive, it will burn earlier than if that fork is wood, right? So those are all the terms that you need to calculate conduction. You need to have the gradient in temperature and the conductivity. All right, that is conduction. So the heat is not moving together with the medium, but it's moving across the medium. What is happening inside the pan when you're burning it or you're warming it from below and you have the water moving around, that is convection. That is a much more effective way of transporting heat, chemicals, anything, right? That is moving together with the water, together with the flow. That's what happens in the atmosphere typically. You don't have conduction because, yeah, it's just turbulent, and we'll see that today. The equivalent for mass to conduction is diffusion, right? So you have diffusion going through gradients. You have, for instance, a gradient in water vapor at the surface, a water vapor at the surface, a water vapor on top in the atmosphere, and the air will move from the land surface. The water vapor will move from the land surface where it has higher concentration water vapor to the air because of the gradient in water vapor and that over average distance of the surface, right? Or times the conductance, as we said before. Thus, diffusion is the same for mass as conduction is for energy, if you wish. All right. And then convection, this is what I mentioned before. So you have radiation, conduction, convection as forms of energy transfer. Okay. Mesoscale breeze. If you remember, if you have two regions of different temperature at the ground, what usually happens is that one of them will warm up the air more. You have air moving up, and the air from the neighboring region that might be wetter comes in to fill in the gap. So you generate some form of cell. We call it mesoscale when in meteorology we talk about 50 kilometer scale or something like that, to differentiate from microscale, micrometeorology, or synoptic scale, which is kind of like fronts, anticyclones, and so on. The mesoscale is like in between, and meteorology we call it like 50 kilometers, for instance, right? So that's a mesoscale. Breeze is the same process that you get in a monsoon. You have the ocean cold, the land warm, and then you generate that convection, right? And then we talked about balloon soundings. You can measure all these properties in the vertical, and people just launch these twice a day in many different regions of the world. Okay, any question? So let's move on to the lecture today. As I said the other day, today's lecture is a little dense and it's not going to be easy. I tried to lighten it a little while I was looking at the slides from last year, but I couldn't really take out much stuff. So I think most of it is quite relevant. So we're just going to try to go through it in not very high pace. Actually, the supplementary that is available in UFRAP for this lecture is very good. So it can actually be a useful source of information. So what are we talking about? We're going to talk about atmospheric dynamics and thermodynamics, concentrating on the atmospheric boundary layer. With the background you got on the last lecture that we just reviewed, you're already able to understand a bit better how the atmosphere boundary layer behaves, how you can calculate the state of the boundary layer in terms of temperature, humidity, CO2 concentration, whatever you care about. and understand kind of like the diurnal cycle of the boundary layer. So that's what we're going to see in this lecture. And again, you've seen this animation before, probably played it today a couple of times because it's important for you to know what we're talking about today. This is the atmospheric boundary layer. This is an example resolution of about 3 meters, 2 seconds. In the video is 1 minute in real time. It's placed in the Netherlands in the summer. And what you're seeing essentially is about midday and temperature, in this case, potential temperature actually. So you can see that the potential temperature is higher at the surface because the atmospheric boundary layer is being warmed up from the surface, like a pan is where it gets warmed up. The atmosphere gets warmed up from the bottom. And it's also being wet from the bottom, of course, being moistened from the bottom. So you see all these plumes of high temperature moving up because the atmosphere is unstable. They become lighter and they move up. And as they move up, eventually they reach the top of the boundary layer. Let me play that again. And when they reach the top of the boundary layer, they essentially scrap a little air from here. You see that you have some of the air from the top of the boundary layer being engulfed into the atmosphere boundary layer. That is because the racing parcels, they have certain momentum. When they reach the top, they essentially overshoot a little and they come back with a bit more air, which implies that the atmospheric boundary layer keeps on growing during the day. As long as you have convection, as long as you have a lot of warm and wet air in the bottom, which generates this convection, the boundary layer will keep on growing and growing, all right? Because it's essentially overshooting here at the inversion and engulfing part of the air that is on top, all right? That top air, we call it the free troposphere, because essentially it's not really affected by humans. It's not really affected much by the ecosystem variability, and it's not affecting us that much. What we really care about is this few 100 meters of atmospheric boundary layer where we live, where ecosystems live, where we have photosynthesis, where we have we experience droughts, heat waves, and so on. So you can see that there is a big inversion on top of the atmospheric boundary layer, right? This is potential temperature, meaning that you have higher potential temperature on top of the atmospheric boundary layer. Doesn't mean that the air warms up when we move up, not in real temperature. This is potential temperature, right? Which is really what we care about. Probably if you were on a plane, 12 kilometers, you know, the temperature outside is gonna be a lot colder, but it's true that there is a little inversion there. So actually, yeah, I'm not sure if I need to draw this, and maybe I failed at drawing it properly, but what you have in potential temperature will be something like this. That's your inversion. What you have in actual temperature, you know, the troposphere temperature goes down with height, and then you will have something like that in actual temperature, presumably, right? So you're correcting the pressure. So still it gets colder as you move up, but in terms of potential temperature, it actually is a lot warmer when you cross the atmospheric boundary layers, because all this in here has been warmed up by the surface, right? So you keep warming it up, and the boundary layer keeps growing. The boundary layer keeps growing throughout the day, right? So essentially, you're warming up a layer that is meant to be stratified, and therefore, by warming it up from the bottom, you're increasing the height of that layer in which you have mixing in the vertical. And that continues as long as you keep warming. All days are just limited, right? So eventually the sun goes down. So that is something that we're going to see in a few minutes. But keep in mind that the air that you have on top of the atmospheric boundary layer is in potential temperature terms warmer. So when you're engulfing this air from the top, as the atmospheric boundary layer grows, you're engulfing warmer air. So that's a heat transfer from the top of the bundle layer, a positive heat transfer. You're warming, in potential terms, you're warming the bundle layer by engulfing that warm air. So you're not just warming the bundle layer from below. Because of warming it from below, the bundle layer grows and also gets warmed up from the top, right? So this entire container in which we have mixing, where we live, where we mix all the air together, and that has kind of like a constant potential temperature, even if it looks like very messy right now, but it's mixed. That is being warmed up from the top, from the bottom, and as a consequence, it also ingests warm air from the top, right? But this is a consequence of this, right? Okay. Now, it's warm and it's dry because the water vapor, like any other contaminant, or most of them, tends to be in the lower layers of the atmosphere because it's being attracted by gravity, right? So most of the water vapor, like all the other air components, and that's why we have more pressure and density of the air next to the surface, is close to the surface. So when you go over the atmospheric bundle layer, there is not that much water vapor. And in addition, all the water vapor that we have in the atmosphere comes from land. Where else is going to come? From the land or the oceans, right? It doesn't come from outer space. So of course, there is much more water vapor in the lower layer, in the atmospheric bundle layer, than there is up here. So the air on top, the free troposphere, warm and dry. And at the bottom is warm and wet here, right? Because you have your sensible and latent heat fluxes. Okay, so you already saw what the atmospheric bundle layer is. It's the last few meters of a few hundred meters of the atmosphere, of the troposphere, which is the lowest layer of the atmosphere. And it can grow up to a few kilometers. If you have a lot of sensible heat flux, like in the tropics or even in a desert, and you have a lot of warming from the bottom, then you can have bundle layers around midday of about 4, 5, 6 kilometers. Here in the summer, you can have about 1 or 2 kilometers, like you saw in the video, that was 1 kilometer actually, right? So homogeneous potential temperature and Q, C is not true really, but I mean, if you look at the profile here, well, certainly there is much more change here than anywhere within the bundle layer. It's true that the bottom layer, which we call the surface layer, and we'll see that in a second, it is not really well mixed. It has a higher humidity and higher temperature because it's there where it's being warmed up. But the moment in which you have sufficiently big turbulence here, all this chunking here, almost up to the surface, is well mixed. I mean, if you were to take the mean of all this, it would be pretty okay, right? I mean, there are some changes in here in temperature, but it's all being well mixed. At least it's mixing. I'm not sure if it is completely well mixed, but we can take that assumption, right? So horizontally, no big changes actually. One thing to point out, horizontally, the changes in the bundle layer change about, like when you have like kilometers, you can have, if you have forest there and a grassland there, okay, but in the horizontal, you don't usually see big changes. The big changes really are here in the vertical, right? Once you cross the inversion and so on. So it's in the process of mixing. I called it there well mixed because we all often call it the mixed layer. Is where the flow adjusts to the surface. I called it there. Well, essentially what it is, yes. It's affected by the surface characteristics, which is friction of the surface, so the roughness of the surface, and the latent and sensible heat fluxes that it's receiving from the surface, right? We have turbulent convection, as you have seen, and I'll mention now just what turbulence is. You probably got it in other lectures, maybe from Nico, but I'll just go very quickly through it. If you haven't, you will, so don't worry about that. And then it is capped by an inversion in potential temperature. If it wasn't like that, it would just fly away. I mean, if you had a layer like that, and then you had on top air that has a lower potential temperature. So if these look like this, actually, instead of like this, it will look like this. What will happen? All this air will just go up, right? So there is no other way. It has to be capped with an inversion in temperature. Otherwise, it will just keep on moving up. The entire layer will go up. So it has to be denser than on top. The lifting condensation level that we mentioned the other day, which was the point at which when you were raising the air, it was condensing, right? Can be in the atmospheric boundary layer, in which case you will form a cloud, or it can be outside, and in that case, the air that rises never reaches it, so you won't form a cloud, right? Theoretically, the lifting condensation level has to be somewhere. If you have some moisture in your air, there will be a point in which you can cool it down enough through the dry adiabatic substrate to actually yield condensation. But the truth is it's not going to go up any higher than the boundary layer height. So if that lifting condensation level is within the atmospheric boundary layer height, you'll have a cloud. If it is outside, then the air won't raise high enough to form a cloud, cool enough to form a cloud and reach that lifting condensation level, right? Because the air doesn't lift higher than the boundary layer height. Yeah, that's going to continue, I think, for the entire lecture. It's not really good time here for this instance. Okay, but that is clear, right? The lifting condensation level, if it is within the atmospheric boundary layer, it means that the raising air that will raise all the way to the top of the boundary layer will actually get to that condensation point. But if it is actually higher than that maximum that they reach, which is the top of the boundary layer, then they won't get condensation. Is that clear? Some of you are looking at me like, what does that mean? Yes, go ahead. If I can talk a bit louder, yes, I can try. Okay, so the atmospheric boundary layer plays a very big role at storing contaminants, storing heat, developing mega heat waves as well, and so on. So essentially, if you were to have, for instance, some pollution being dropped in here, you know that it's going to mix throughout this container. It's not going to go any farther. So if you drop your pollution here, you have a cap that is going to imply that all that pollution is going to stay close to the surface. It's not going to go any higher, which is a problem because you're not diluting that pollution within a larger container, right? That's why when you look at cities, you sometimes see like the bottom of the city super dark. That's it, boundary layer height, right? So the first figure you have in the slides actually does the boundary layer height, all the contaminants of the cars and so on below. If that boundary layer height is very high that day, lucky you're actually able to dilute those contaminants a bit better. If that is very close to the surface, that's where all the contaminants are going to stay trapped. There is only one option, is that you can actually pump the contaminants higher than the atmospheric boundary layer height and just get to the free troposphere, and then they catch what we call the geostrophic winds, which is the horizontal winds like planes take and so on, in the free troposphere, and that goes super fast somewhere else, and then your pollution may end up in China. It doesn't matter. But that's the only thing that you could actually do. Try to actually emit your pollution either high enough or at high enough temperature that it goes super fast up, breaks the atmospheric boundary layer, and then leads through the free troposphere. Okay. So maybe one note about turbulence, which is something that I think that if you haven't seen, you will see. Anyway, you have two types of flow, okay? You can have essentially laminar flow or turbulent flow. I'm simplifying things, but essentially laminar flow is when you have the flow paths being parallel, typically slow. So you have kind of like what you have in, for instance, plants with the hydraulic transport in the xylem, that's laminar. You have kind of like parallel pathways, there is no facts mixing, the flow is typically slower, and so on. Or you can have turbulence, which is what you just saw in the video, which is a much more dynamic and fast mechanism that is much more efficient than mixing heat, temperature, heat or moisture or CO2 or whatever you care about. So that is turbulent flow, correct? You can actually know whether a flow is going to be turbulent or laminar. That depends on its temperature, on its velocity, and it depends on its viscosity. So the viscosity of the fluid is going to actually make it harder. It has high viscosity to generate turbulence. If it has a low viscosity, the flow can be more turbulent, all right? So you can think of, for instance, some very viscous liquid like mercury, for instance. It would be really hard to actually generate the turbulence that you just saw. The air has very low viscosity, so it's easy to generate turbulence. The way in which we can actually discriminate whether a flow is going to tend to be turbulent or not is this Reynolds number that you have in there. The Reynolds number is actually named after Osborne Reynolds, which is this guy here. It's just essentially what I mentioned is the flow velocity times some form of length scale. That is the reference length scale. In the case of the atmospheric boundary layer, it would be the atmospheric boundary layer height. In the case of a river, it would be the water depth of the river and the viscosity of the fluid. So if you have very high Reynolds numbers, that fluid will tend to flow in a turbulent fashion. Now, the atmosphere almost always flows in a turbulent fashion because you have high velocity of the winds, relatively high, and the air is not very viscous. So you actually tend to have that, okay? Especially in the atmospheric boundary layer. And why especially in the atmospheric boundary layer? Because the free troposphere, you can have super fast winds as well, but they tend to be more laminar, more parallel to each other. Well, in the atmospheric boundary layer, because we are disturbing the flux of the flow of the fluid by essentially what we mentioned, friction, warming and moistening and convergence and so on, all these processes that generate essentially a break in the laminar flow that originates the turbulence. Because in reality, and despite what the Reynolds number says, it's not just about the velocity of the fluid and the viscosity of the fluid, it's also about whether you actually inject some energy to generate that turbulence first and to maintain it. And that energy, in the case of the boundary layer, it comes from the warming from the surface, it comes from the moistening from the surface, it comes from the friction. So eddies, which are these big square-leaf patterns that you see there, they require some energy to be fueled and to be maintained, because otherwise they automatically break into smaller eddies until they get actually dissolved by the viscosity of the fluid and then they disappear. So you need to have high velocity of the flow. You need to have a fluid that is not viscous, and you need to have some energy introduced, and we have that in the boundary layer. So that's why the boundary layer is so turbulent. Now, the problem of turbulence is that it's super difficult to mathematically represent. It's hard to make a model of the processes that you saw before because they occur at a very, very high spatial and temporal resolution, all right? So it's a super chaotic, complex process to actually describe in an accurate manner. So we usually go for more simplifications, statistical methods, and so on, and that's what we are going to see next, actually. But you'll see this. So I just mentioned this, but just to recap, the land surface is essentially creating turbulence by warming and moistening. That is buoyancy. So it's generating a positive buoyancy, it's making the air lighter, which is going to make it go up. So then you start generating that turbulence, you start having that convective upwards motion, or by friction. The roughness of the surface is going to essentially slow down the flow next to it, and that's going to generate the swirly patterns, friction eddies, and the air is going to move up, all right? So friction and buoyancy is the two means in which the land surface essentially breaks the laminar flow, causes turbulence, causes parcels of air to move up, and generates all this convection in the atmospheric boundary layer that gets it to grow, right? So it's the land surface that makes the boundary layer, right? Okay, That happens, by the way, in any, and actually the terminology boundary layer is not result from meteorology. You can have boundary layers in pipes, you can have boundary layers in rivers, in anything that flows and then has some friction on the bottom, for instance, is going to actually generate that boundary layer. So yeah, we have the buoyancy and the friction generating that energy that is needed to actually generate the convection. So I was saying that the land surface actually is just generating this boundary layer that happens in any other place on Earth where we have a flow, kind of like rivers, oceans, pipes, even in trees and so on, because there is a point in which that flow has to adjust to the conditions of the wall that is containing them, which is essentially implying that there, just at the surface level, you have a flow that is zero, right? Now, flow. That's due to the friction, essentially, right? So if you think of a pipe, for instance, maybe I can draw that here, but you probably know it. If you have a pipe like this, in which you have two walls, right? And the flow goes in this direction, the flow velocity is going to look like this, right? And that has to do, this actually loss in flow velocity has to do with the friction of the walls. If you have a river, this will also look like this. Won't actually look completely like this because it also has some friction from the earth, so it will kind of like this. And the maximum velocity will be a little higher, like 70% instead of 50%. But you always have kind of like the layer in which the flow is actually adjusting to the surface conditions, because essentially it cannot do otherwise. And we'll go through that later in a second. But that's what we call in fluid dynamics a boundary layer. It doesn't need to be for meteorology, but in the case of the atmosphere, it's our atmospheric boundary layer. And as I say, there we have the turbulence, both mechanical and buoyancy turbulence, all right? Okay. So I said the other day this, but I'm going to repeat it. Like the latent and sensible heat fluxes are so important in this course. The land surface latent and sensible heat fluxes, they get initiated through, in the case of a sensible heat flux, conduction, because it's a conduction of the temperature from the surface to the air, because that cannot be convection. It cannot be the surface jumping and moving the heat. So that first stage is a conduction, then is convection, right? That convection occurs through turbulence, right? The same for the latent heat. You have first diffusion of moisture, and then you have convection, also turbulent. And that's why we call them the turbulent heat fluxes. So the latent heat flux and the sensible heat flux, we usually call them turbulent heat fluxes, right? As opposed to, for instance, and you have already seen the energy balance, so you will see it later in the course, but you may remember the ground heat flux, which is when you warm the surface and then there is heat going down. That is just conduction and it's not turbulent, because only convection can be turbulent, all right? So, the daily cycle. Let me just give you a bit of an idea of how the daily cycle of the boundary layer works, because it's not too difficult. So if we place ourselves, probably the easiest is in the sunrise. So here, actually, this is sunrise. So you start having the sun's energy warming the land surface. So what do we have? Remember your energy balance partitioning, we essentially have latent and sensible heat fluxes coming, right? So we're warming and wetting the air here. Fair enough. So that is going to start generating some vertical motion progressively, more and more, because you're warming more and more the surface with the sunlight, and that makes it grow because it's essentially generating these vertical motion, those eddies that are overshooting the top of the atmosphere, which essentially will be initially at ground level. And then as you warm up, keeping on growing because it's entraining, we call it entrainment. When we engulf air from the top of the boundary layer, we call it entrainment. And you'll see it later that word comes in quite a few times actually. So we keep on entraining air from the top of the boundary layer, and that makes it grow, We're increasing the size of the container because we are pulling in more air into the container, right? So that keeps on growing and growing and growing as long as we have the sun warming the land surface, right? Eventually, at sunset, we're here. What happens is that the sun goes and the surface keeps on emitting long wave radiation, right? It's been emitting it all the time, but now, of course, it's more dominant because the sun is not there, so it's cooling down. So the surface cools down, and eventually, since it's cooling down, it's starting to cool down also the air on top. That's what we call a negative sensible heat flux. So instead of being air being warmed up from the surface, is the surface being, in this case, warmed up by the air, because the air is actually warmer than the surface. So the moment in which the surface gets colder than the air on top, the sensible heat flux goes down, all right? And then the air starts cooling down because it's losing the energy that is actually going towards the surface. So you start losing air temperature because the surface is no longer being warmed up and warming up the air on top, but actually, in fact, since it's emitting long wave, it's cooling down, and at some point it's even colder than the air on top, and then the sensible heat flux starts pointing down and the air starts cooling. That's why the air cools down at night, right? So essentially it's just pointing towards the surface, all the heat that it has been absorbing during the day, or taking from the surface during the day. So what happens that air that is cooling suddenly becomes super dense and stable because it won't go up any longer. So you generate an inversion. This is an inversion. And of course it grows because that cooling keeps on going. So there is more cooling of the air next to the surface, and therefore that layer of stable air is going to keep on growing until sunrise. Sunrise, we generate a new, brand new atmospheric boundary layer. We call it convective boundary layer to the day atmospheric boundary layer, but it doesn't matter. If you use convective or atmospheric boundary layer, some people call it planetary boundary layer. It's the same thing. Don't care too much about it. But then at sunrise, what happens is that you start again warming the surface, and then you start generating again a nova boundary layer. Eventually, of course, you start engulfing. Well, actually, that's what you're doing at the beginning. You are entraining the nocturnal boundary layer. And then eventually you start entraining this residual layer, which is the same as the boundary layer from the previous day. So the boundary layer from the previous day is still there, up over our heads. At some point in the next day, you start entraining it, you start engulfing it again. And then it gets again back in contact with the land surface. All right? So maybe it's easier to do it this way, really, in which you have a little nocturnal boundary layer, and then it breaks, and then you have another nocturnal boundary layer, then it breaks, and so on. That's actually quite important for heat waves, because if you have all the air being warmed up during the day because of the sensible heat, and also the entrainment that it causes from the top, right? All that warm up air at night, of course, here it gets colder during the heat waves. It's nice, about 10 degrees colder. But all that heat actually hasn't moved anywhere. It's actually 500 meters over our heads in the residual layer, waiting to be re-engulfed again the next day into the new atmospheric boundary layer, and it gets again in contact with the land surface, and it keeps on being warmed up. And that's why we have a progressive heat accumulation. So at night, you have your nocturnal boundary layer, it gets colder, it's an inversion, but then the heat that has been accumulated, that you're not feeling any longer, is 500 meters over your head, waiting to be re-engulfed in the next day into the atmospheric boundary layer, and then it gets again in contact with you, of course, and then you keep on warming that during the day because of the sensible heat flux. Right? Did I miss anything that I wanted to mention? Probably not. Okay, So maybe now you understand this a bit better. Again, this is just an example, but it's quite representative of how the boundary layer behaves in these latitudes in the summertime. So yeah, it's just constant growth during the day. Actually, I didn't show you, but this is probably just a few, how many minutes? Well, you could calculate it, but it's probably like an hour or something like that in real time. But you can see the boundary layer has grown. You didn't see it during the video, but now it's about 1 kilometer. And if you go actually to the, sorry for that. If you go actually to that's the end of the video. If it wants to work, yeah. In the beginning of the video, it was actually lower. It was like 800 meters, something like that. And now it has been growing up because it's been entraining air from the top in just 1 hour, okay? So as I mentioned before, it's super hard to actually model the processes in a physical manner because they occur super fast and at very small scales. So turbulence is really difficult to actually represent by physical equations. We can simplify things, and that's what we are going to do in the practicals. The model that you're going to use in your practicals is called CLASS, is a mixed layer theory model, and that mixed layer theory is what we're going to see now. So this is an example, CLASS is an example of what we're going to see next, actually. So what we're going to do is simplify all these turbulent processes, which are really hard to model, and represent them in a way that is actually very simple, which is assuming that the entire atmospheric boundary layer is well mixed, and therefore the temperature, potential temperature, and humidity are constant, right? So they don't change with height until the inversion. Big assumption, well, still okay. If we look at it here, maybe it looks worse than this. Maybe if we look actually at this, it's kind of like homogeneous for the entire thing, not big horizontal changes. In the vertical is well mixed, except for, of course, after the inversion. Maybe the land surface, we don't do a good job because it's actually warmer and wetter than the rest of the layer. Processes that we care, if we want to do that, we care about the radiation. Of course, we have to know what the radiation is. We need to know what the land surface heat fluxes, the turbulent heat fluxes are, the latent and sensible heat flux. We need to know how much advection comes in from the horizontal if you have a lot of heat advection, but usually that's a less important term, actually, because even if it has a lot, there is a lot coming, there is also a lot leaving, and what you care about is the budget, as I mentioned before. And then we care about how much we are entraining from the top of the boundary layer, which would be entrainment heat flux, but also the moisture, which will be negative because it will be wetter within the atmospheric boundary layer than on top. So when you entrain air from the top of the boundary layer, you're actually having a negative moisture flux into the layer, into the mixed layer, right? So you're actually making it drier. You're making it warmer and drier because the air on top is warm and dry, right? And then I have another concept there, which is the subsidence. You're going to see it later in the practicals. It's more for meteorology for the course that you'll have next year with Hans Verbeek. But subsidence is kind of like the large-scale tendency of the atmosphere to press or to depress, if you wish. That's essentially when you see high pressures like anticyclones in your weather maps. That means that the high pressure is essentially putting the atmosphere towards the ground. So it's kind of like a general tendency that if that is the case and the general atmospheric circulation at the large scale implies that the atmosphere is being compressed, for the atmospheric boundary layer to grow, it would be a little harder. If on the other hand, you have a low pressure system, like a cyclone, then it's going to tend to move up. Then the growth of the atmospheric boundary layer will be a lot more enabled, it will be easier. So that actually matters to some degree, that subsidence, that could be, as I say, in the direction to press it, positive subsidence or negative subsidence. An anticyclone, high pressures, implies this, and cyclone, low pressures, implies the opposite, okay? So essentially you have the anticyclone conditions, and this is maybe a little confusing if I don't explain it. In the anticyclone conditions, you have that compression, but because you have actually clear skies and warm temperatures, the boundary layer grows more. You have more sensible heat, more latent heat, more dynamics, and despite the fact that you have that positive subsidence, essentially compressing the atmosphere, you have that growth of the atmospheric boundary layer. And the opposite, when you have a cyclone, you have cloudy skies. Even if the atmosphere has a low pressure, so it will grow easier. The truth is that because you don't have a lot of latent and sensible heat flux, because there is not enough radiation, then of course it grows less than it will grow otherwise. So typically during anticyclone clear skies, you have a higher atmospheric boundary layer, despite the fact that you have subsidence, positive subsidence. All right. That I think is his way of actually trying to do it without making a lot of noise. So just have to deal with it, I guess. So maybe one thing to mention that is important is that the, of course, the mixed layer model is a simplification that I already mentioned it. The surface layer, as you can see here, is not going to be well represented. This is something that I mentioned already, but what you're seeing here is the black is kind of like the real, if you wish, is a little, of course, idealized, but the real profile of humidity in the atmosphere. And this is the real profile of potential temperature in the atmosphere. So you can see actually the atmospheric inversion here. You have a jump in temperature, kind of like what I was drawing here before, right? And then you have a gradient in potential temperature with height. So this is actually in potential temperature terms colder, and that's why it doesn't move up. In the case of humidity, we mentioned that we have higher humidity next to the ground in the atmospheric boundary layer, and then the air is dry on top of the atmospheric boundary layer. So that's what we have explained before, and it's probably easier to view it this way, right? But you can see that the land surface in contact with the air on top, it actually provides a lot of moisture and heat, and that causes this mixed layer not to be actually well represented by a straight line in the case of what we call the surface layer. That surface layer, I didn't mention it, but it's actually here. You see, it's a part of the atmospheric boundary layer, but it's just a few meters, like a few tenths of meters, like 50 meters, something like that. It's usually about 0.1 the boundary layer, so 10% of the boundary layer. And I'll tell you what that surface layer is, because maybe I can already mention that in that surface layer, what really matters is the friction, and it doesn't really behave like the rest. And you can see it already here, that it doesn't actually, that there won't be such a powerful mixing there, because essentially you have the friction in preventing that mixing to occur, because you won't have the same amount of wind and vertical motion next to the ground, because you have the friction, the roughness of the surface. So there, that friction will generate these gradients that you see here, because essentially you have less movement of air next to the ground because of the friction. And in addition, the layer is being warmed and wet from below. So therefore, that will generate actually a higher temperature and a higher humidity next to the ground than just on top. You saw it in the simulations, but it comes across quite clear when you look at these profiles. And that means that the mixed layer theory and the model that you will use during the lectures won't be ideal for the last few tens of meters of the atmosphere, because there the friction is really what dominates. And there you need a different type of simplification, which is called the logarithmic wind profile, which is what we will see later after the break, okay? But let's go back to the mixed layer theory. So how can we represent this like this, essentially? You can see the red line and the blue line. So essentially, we're going to represent the entire evolution in time of the mixed layer as if it was just one single value of humidity and one single value of temperature in time. And of course, these are going to be growing or not during time. And then you have to also bear in mind that this is going to be determining to what degree you're entraining heat and moisture as it grows. So it seems like an easy model. You're warming it from below, You're diluting that heat within the atmospheric underlayer container. So if it's big, it will be more diluted. Then that keeps on growing, and as it goes, it's entraining this air that is dry and warm. So let's see if we can actually get to model that, which is of course a lot easier than to model all the turbulence. But if you were super brave and wanted to model all the turbulence, like you saw in the previous simulation, because that's an actual simulation of turbulence, the video that you saw, what would you require? And I'm explaining this because it's a start point to simplify with the mixed layer theory. You would require the energy conservation, mass conservation, momentum conservation, and the gas law of ideal gases. Those four equations are really the backbone of every climate model, any numerical weather prediction model, weather forecasts, and so on. Those four equations: the conservation of energy, mass, momentum, and also the ideal law of gases, okay? Or the law of ideal gases. Okay, so the law of ideal gases, you remember it from the other day. The energy conservation implies that if you have more energy coming than leaving, then the temperature might go up or it may evaporate. Mass conservation, like the water balance equation, if you have more water coming than leaving, then you have an increase in moisture content. If it is the atmosphere in the specific humidity, for instance, or water vapor pressure. Momentum conservation, momentum is just mass times velocity. For the air, you usually think of density times velocity because the mass requires volume, is a bit weird, right? Density, density times velocity. So that also needs to be conserved, the momentum, as we'll see in a second. All right. So if we want to think about energy, we usually diagnose it with temperature, potential temperature, right? Sensible heat flux, potential temperature. We think about water, we think in the atmosphere of humidity. That could be in terms of specific humidity, so kilograms, or it can be in terms of pressures, so water vapor pressure. But yeah. And then if we think about momentum, then we usually think about winds, velocity of the wind and so on. Mass conservation, of course, it applies to water vapor, but it also applies to any other constituent. It could be CO2, anything, any substance that has a mass, right? Good. So we want to know the state of the ADL. We know that solving these equations is difficult, so we're going to see how we can actually do it more simple. But the start point of these equations, if you wanted to actually put all these equations, well, not the law of ideal gases, but the conservation equations in one single generic equation, it would be this one. That essentially applies to anything. It applies to energy, it applies to mass, and it applies to momentum. What I'm using here is that phi sign is actually just a generic variable. You can replace it for humidity, you can replace it for temperature, you can replace it for wind velocity if you are interested in momentum, if you're interested about the energy or the mass. You can replace it for CO2 concentration. So essentially describing your state variable changes in time as a function of fluxes. So let's go through it just a second to make sure that we are all on the same page. By the way, the momentum conservation equation is called the Navier-Stokes equation. If you haven't seen it yet with Nico, unfortunately for you, he will actually derive them and so on. So this generic form of the conservation equations, again, you can think of these as any variable that you want of your diagnostic variables or the state variables. What do we call the state variables? As we mentioned in the first lecture, for energy, the temperature, the atmosphere, potential temperature would be better. So potential temperature, we're going to think about specific humidity instead of water vapor pressure. So Q, potential temperature, Q, for the momentum density times velocity of the wind in one direction to make it easier. So that will be your energy mass, because we care more about the water vapor, but you could do argon or whatever gas that you care about, CO2, of course, and momentum, right? So those momentum is density times velocity. So those you can replace them here, and you will have your conservation equation of mass or your energy conservation or your momentum conservation equation. So it's a generic way to actually represent all these three equations in just one. And what it's telling you is that the changes in time, to simplify, we're going to think of temperature, potential temperature, the safe temperature. So the changes in temperature in time are going to be equal to the amount of flow of temperature in all directions. That's what this is telling you. This is the change in temperature in the X, change in temperature Y, the change in temperature in the Z, right? So 3 directions times the wind in each of the directions. Why times the wind? Because we're thinking of convective turbulent processes. We're thinking of transports in which we have convection, in which the transfer of temperature occurs with the medium itself. We're not thinking about diffusion and conduction. In fact, if you wanted to also write the diffusion and conduction here, you could, but it would be a waste of time because in the atmosphere, the conduction and the diffusion are pretty much nothing. It's all moved through the winds, really. So we forget about the conduction and the diffusion. We make it the equation of conservation a little easier. We think that it's just the movement of the wind. So if the air temperature changes in time, it's because you have got wind that is warm coming from different directions. So if there is more warm wind coming than leaving, then you have a positive temperature change in time. Warm air, and actually talking about heat fluxes, right? To be a bit more precise. So you have the heat fluxes in all directions. If they are actually net positive, they cause a temperature change. That's what this equation is telling you. We said also the other day, when we saw the first law of thermodynamics, that is another way of seeing this conservation equation, that also, in addition to actually using the energy to warm up, you can use it to evaporate, for instance. What that goes in here is this S. Those are actually specific processes for the momentum, mass, or energy that we put in there. So this is like applicable to all three, but this one is just for momentum, which is the forces per mass, and this one is just for mass and energy. An example of something specific for energy, latent heat. Doesn't apply to momentum, it doesn't apply to mass, that's why you're trying to mass. But so, so in your first law of thermodynamics, which is an energy conservation equation, you can think of the energy coming from the different sides, from outside, causing a change in temperature and some evaporation. And we said also the pressure change. So essentially, the equation, you saw the first equation, the first thermodynamic equation, that's actually an energy conservation equation just like this one. Right? Okay, so let's start with this. It doesn't really look too nice. You need to know the fluxes in all directions. If we care about the humidity and temperature of the atmospheric boundary layer, that's quite difficult to model, but that's actually what will be resolved by the model in which you saw the simulation with the wind, the turbulence and so on. The video that you saw before is actually resolving this equation, in particular for humidity, for temperature, for momentum, and so on. But as I said, we are not going to be able to apply this usually. You need to have very, very high resolution, very high computer power, and you cannot do it for a large region. So mixed layer theory aims to actually simplify this equation, which is just bare physics, by taking a few assumptions. And the assumptions are 3, and you have them in the first one is what we call the Reynolds decomposition. Now, Reynolds decomposition is a fancy way of calling something very simple. Is that if you have a time series of something, you can take out the mean, and then you end up with a fluctuating component, right? So it's kind of like when you look at seasonal patterns, you take out the seasonality and you look at the fluctuation. So if we were to look at, for instance, it doesn't need to be a time series really. It could be a change of anything in time. You have a time series like this. You take out the mean, which is this, and you end up with some fluctuating component that is average 0, that looks like this. Well, Well, you're just decomposing, right? So you're decomposing the signal into one average value plus everything else, right? And that is quite convenient to do. So let's just keep in mind that we do that. And the reason we're doing that is because the mean component can go, you can cross the layer and just keep the fluctuating component, but you'll see that in a second. So we do that Reynolds decomposition, separate the fluctuating component and the mean. Second thing we do is we assume that the vertical is actually represented by one single value. And you saw it before, it's just one single line. So we are assuming that it's kind of like homogeneous in the vertical for the mixed layer. So we care about the vertical variability in the sense that we care about the mixed layer, and then we have the jump, then we have the gradient of the free troposphere. But we are going to assume that it's well mixed. So that is the same humidity and the same temperature for the entire atmospheric underlayer. All right, so that's another assumption. It's well mixed. That's why it's called well mixed or mixed layer theory. And the third assumption is that horizontally is homogeneous. What does it mean? That we don't have big changes in horizontal. We saw it before. It's kind of like if you were to take actually a horizontal, like a mean of all the vertical, you would end up with one line. It doesn't really have big changes in the horizontal. So if we assume that, and in addition, and that is why we wanted the Reynolds decomposition, we assume that the vertical wind, the average of that vertical wind is 0. And why is it 0? Because of course you have wind going up, but also wind going down. So essentially, you can say, well, what we have is a lot of fluctuations in wind direction, wind velocity in the vertical, but we don't have actually a net wind in the vertical. Essentially cancels out the wind up and wind down, they cancel each other out. So essentially the mean wind is 0, and then we only care about the fluctuations in the vertical wind. So we don't care about the horizontal components of the fluxes. We only care about the vertical and precisely about the fluctuations in the vertical, not the mean. So then of course this equation becomes super easy. It becomes just this. You get rid of your horizontal components, no horizontal components. Your vertical component becomes just the fluctuations. And therefore, you only have the change in, let's call it temperature, for instance, in time, being a function of these vertical fluctuations in wind. Now, what are those vertical fluctuations in wind? So, those are essentially turbulent fluxes. If you're thinking of heat, the sensible heat flux, or if you're thinking of vapor laden heat flux, those are fluctuations of vertical wind with temperature or fluctuations of vertical wind with humidity, right? So the covariance, if you wish, the product of the fluctuation in vertical wind to the product of the humidity fluctuation, for instance, the covariance of the wind to the vertical component, the fluctuation to the wind, and the humidity, that would be your latent heat flux. The wind moving up, bringing moisture, that's your latent heat flux. Your wind moving up, bringing temperature, that's your sensible heat flux. And the wind moving up, bringing momentum, that's your momentum flux, right? Because you can also have wind moving up, bringing horizontal wind times density up, because momentum is also transferred and it also needs to be conserved. Right? So essentially, that is what this is telling you, that you have changes in that vertical fluctuation causing changes in time. So essentially, the heat fluxes are causing the changes in time. So we're slowly getting to something a lot simpler. Now, we have this theta here, which doesn't make any sense because we're assuming that we have a vertical, homogeneous temperature, humidity. We don't need to have a theta there. So what we can do is integrate over the vertical, like we did here. So we are assuming this. And then we get rid of the theta. This is coming out super weird in my slides, but also in yours, because every time I say that, for whatever reason, this goes down. There is a minus here. And I don't know how to fix it actually. I should probably just put an image because this is some weird thing. So I think you probably have the bracket right, but you miss the minus because the minus is down as a subscript probably. So there is a minus right here. Maybe the next one is fine. I'm not sure actually. No, it's also wrong. Also, the next slide is wrong. This minus goes to the subscript for whatever reason, and you don't see it, and you think it's a product. So there's a reason why that is minus. I mean, if you want, we can go through the integration, but essentially what you're doing is integrating this equation between two heights, the bottom and the top of the boundary layer, and that's it, right? So if you integrate this equation between those two heights, essentially you have the flux at the surface divided by the height, which is the difference between the two heights, the height of the boundary layer, minus the same thing, but at the top. So the bottom minus the top. And you don't have the top minus the bottom because in reality it's the top minus the bottom, but you send it to the other side of the equation, so then it gets a minus. And that's why you end up with this. So if you integrate this, trust me, you can try it at home. It just gives you this here. Right? So what is that? That is the mixed layer equation. And it has two components there. This, so the wind fluctuations with, for instance, temperature in the vertical at the level 0 is your sensible heat flux, surface sensible heat flux. If this is instead of temperature, humidity is your latent heat flux, your evaporation. And minus the same but for the top, that's your entrainment, right? Of moisture or heat. So that's the flux from the top of the boundary layer. So you have those two fluxes. And of course, they get diluted by the height of the container. If you have same amount of fluxes and the boundary layer is smaller, then they cause a bigger change in time of your variable than if you had actually a bigger container, because you dilute the effect with a bigger container. So if we think of temperature, the temperature changes in time will be equal to how much you warm from the bottom, how much you warm from the top, and how much is diluted within the height of the boundary layer, the container size. You will have a higher change in temperature if you warm from the bottom and the top the same, but your boundary layer's height is smaller because it doesn't get diluted so much. That's why you have the H down here. So suddenly you can actually model the state of the atmospheric boundary layer, temperature, but also humidity, momentum, if you wish, CO2 concentration. It also works by knowing just the fluxes from the bottom, the fluxes from the top, and the height. And that's essentially what the mixed layer theory allows you to do. Based on very few assumptions, essentially that homogeneously in the horizontal, so we don't care about the horizontal, and well mixed in the vertical, and that's it. That's essentially what you're assuming there. Okay, that is what you will use in your practicals. And there is one thing here that is still a little difficult to grasp, maybe, is the entrainment flux. Because of course, how do you actually get to know the entrainment flux? So the flux from the top of the boundary layer as it grows, how much heat, for instance, if you want to think of heat, how much heat is that implying? How much flux of heat is that implying? So that heat flux from the top will be a function of two things. How much air you're ingesting and how warm it is, right? If you ingest a lot of air and it's very warm, you have a very big heat flux from the top, right? If from the top you're ingesting little air and it's not warm, then of course the heat flux from the top is low. So the heat flux from the top, this entrainment heat flux, is only dependent on two things: how much air you're entraining and how warm it is. All right? But you have to actually model that heat entrainment. So this is the equation that does it. You have how warm the air is, which is just a function of the jump here. If this is big, it implies that the air is going to be warmer, right? And how big it is, this is just a change in height in time. So how much it has grown, if you think of one single time step, how much it has grown, the boundary layer height, so how much it has grown, and what was the temperature of the air that it ingested, right? So volume of air ingested and temperature of the air ingested. And that is just dependent on this jump, this delta theta, which is telling you how warm it is in the free troposphere compared to the atmospheric boundary layer, and how much you have grown. So what is the difference between this H1 and this H0, if you wish? So that's going to give you this. And this term in here, which by the way, the S is a subscript, is again one thing that when I say it changes for whatever reason, you have it here, subsidence, it's just a substance, all right? It's just to correct for this effect of subsidence that I mentioned before, that if you have high pressures, you have a tendency to press the surface and therefore it will grow less. And if you have low pressures, it's easier for the boundary layer to grow. So that's why this is actually corrected from the delta H latent, which is the differential of H, the increase in height and time of the boundary layer. So that's how you calculate your entrainment flux. And one thing to bear in mind is that you need to know this, the growth of the boundary layer in time, which is in here. What is that dependent on? It's dependent on the surface fluxes, right? You'll have a stronger growth of the atmospheric boundary layer when you have bigger latent and sensible heat fluxes. We said it before that the boundary layer grows because of the surface effect, because it's being warmed up and wet from the bottom. So the surface fluxes are going to determine the degree to which it grows. All right. So if you need to calculate the growth of the atmospheric boundary layer in time, you need to know the surface fluxes. This beta is just a constant, forget about it. The surface fluxes, but you still need to bear in mind the jump in that. And why is that? Because it's easier to grow against the smaller inversion than against the high inversion. So it's easier to grow when you have that than when you have this. So this is, imagine this is temperature, potential temperature. So you want to ingest the temperature on top. If you have the temperature on top that is much warmer than the atmospheric boundary layer, then of course it's a lot harder to engulf that air because it's much lighter and you're super dense. So you're trying, there's a big difference in density between the two layers. If the big difference in density between the two layers is very small, like here, it's a lot easier for that bottom layer to engulf air and entrain it from the top. That's why you have here this term, the jump, controlling the height. So essentially the jump comes twice and it kind of like cancels out for the entrainment. Because first, if you have a big jump, so if this is big, it's gonna be harder to grow. But on the other hand, as it grows, it will be entraining warmer air. So for the entrainment heat flux, having a higher jump implies that you ingest less air that is warmer. So kind of like balances out this effect, right? For the entrainment heat flux. So you're, in one case, if you have a small jump, you're ingesting more air that is less warm. And in the other case, if the jump is large, you will be ingesting less air, but that air will be warmer. So in terms of the absolute sensible heat that you get, so the heat flux from the entrainment zone, that will be equivalent. Is that clear? Yeah. Okay, and maybe the last thing to mention, but Irina will go through this later in the practicals, is that of course the growth of this jump, if we now focus on this jump, is actually proportional to this slope. The slope is given by this gamma, which is not the psychrometric constant that you saw last week. Sometimes I use similar or the same symbols to refer to different things in different lectures, and that has to do with the fact that this is interdisciplinary, and there are topics for which we use the same symbols because we just don't have more. But this here, which is not the psychromatic constant, it's just the slope of this. And if the slope is like this or like this, as you progress in time, the jump will be different. Probably close. I'm getting better. If this is time 0, and this starts growing, at time 1, this jump is going to be larger than this jump. So essentially, the slope of this, which is the last rate in the free troposphere, is going to determine the evolution of the jump. And that's what this is telling you. The jump will be proportional. The evolution of the jump will be proportional to this slope, this lapse rate. Because if it is very steep, the next step, the jump is going to keep on growing more than if it is very steep. That's what you call it. But you got it. Yeah. So now, let's see if we understood. So this is the question, and then we will take a break. So at sunrise, the surface and the Earth, we're saying that they work faster than the midday. And that is despite the fact that during the midday, during noon, of course, the solar incoming radiation is a lot larger, right? So how can it be actually that when we're in the morning and we're receiving less sunlight, the air is warming up in time faster than it will warm up later, okay? So the options are, the surface is warm relative to the air in the morning, you see. So there is larger heat flux. The CBL, so the convective boundary layer, the atmospheric boundary layer, the boundary layer, if you wish to call it, it doesn't matter. The boundary layer is shallower in the morning, so there is less volume to warm up. Low winds in the morning imply that hot air is not blown away. It takes less energy to warm the air when it's colder. And the E Alus likes it this way. And by the way, there are 20 different gods of air in the Greek mythology. I didn't know. Depending on where the air comes from, you have a different, and the strength and the velocity of the air, you have a different god. Same for the Romans. They didn't get smarter. So who wants A? The surface warm relative to the air, so there is a larger heat flux. No, didn't convince you, that's good. The boundary layer is shallower, so there is less volume to warm up. Come on, don't be shy. Yeah, see some hands very shyly raising. Low winds in the morning imply the hot air is not blown away. Didn't convince you. It takes less energy to warm the air when it's colder. No? So what about, are you guys the rest just going for E, or you're going for E? Okay, now the right answer, as some of you understood, is the B. But let's actually disqualify the others first. So the surface is warm relative to the air. In the morning, well, yeah, you will get warmer relative to the air, but that doesn't really mean much. Actually, the sensible heat flux is larger in midday because the surface is super warm. Low winds in the morning imply hot air is not blown away. Well, if it was blown away, it would just be coming from the surrounding regions that will be experiencing the same. So that's why horizontal processes don't matter in this case too much, right? So no, it's not really what happens. It takes less energy to warm the air when it's colder. This is not total bullshit, it's true. Actually, it's not a reason because it's just a small thing, but it's true that the specific heat depends on temperature. And it's true that it takes a little less energy to warm the air by 1 degree when it's colder. So specific heat is actually a little lower when it's cold, right? But the right answer is that the boundary layer is shallower in the morning. So of course you have less volume to warm up. The container is smaller. So if you have the same fluxes, if we go back actually to this equation, maybe it comes out clear. If you were to have equivalent fluxes from the surface and from the top, of course the height of the boundary layer is determined. If you have actually a very shallow boundary layer, you warm it up much faster. And in the morning, it's actually inexistent. It's just starting to grow, the boundary layer. So that is the reason. And we're going to stop here. We're going to have a break, 15 minutes, let you breathe, and then we'll continue there. Okay, any questions? Nope. Okay, that was a little dense. I'm aware of it. We'll go through, well, we'll review it beginning of the next lecture, but also if you want to stop me at any time later, that's also fine. Okay. All right. So we've seen the mixed layer model and the mixed layer theory. And we talked about the simplifications to represent the atmospheric boundary layer with this mixed layer theory. Now, we also mentioned that in the bottom of the atmospheric boundary layer, the conditions of the mixed layer do not really apply. We cannot assume it's actually well mixed because we have all the heat and moisture coming from the bottom, and we have little wind in that to actually move it up. So what we will usually encounter is something like this, like a profile of humidity and temperature that declines with height until what we call the end of the surface layer. So we're going to see now how to actually represent that surface layer, which is just the bottom of the boundary layer. So we said that the troposphere is the lowest layer of the atmosphere. Boundary layer is just the last few 1-2 kilometers. The surface layer is just the last few meters. We're talking about 10 meters, 20 meters, okay? That's what we call the surface layer. That is also part of the atmospheric boundary layer, which is also part of the troposphere, which is of course part of the atmosphere. And that surface layer is essentially where we are right now. We're subject, or we are exerting friction on the passing air. We are evaporating and we are warming up through sensible heat flux the atmosphere. And that generates essentially a bit different dynamics than what we find right above in the mixed layer of the atmospheric layer. So the same way that we mentioned that in the mixed layer, we have constant temperature and constant humidity with height. In the surface layer, we have constant fluxes, and we'll see why. Okay, just keep that in the back of your head for later. And we mentioned, and I already mentioned it before, that the simplification that we take to represent the processes in the surface layer is the logarithmic wind profile, typically. And we'll go to see what that actually means. So the same way that we use the mixed layer theory to understand and simplify the turbulence in the mixed layer for the lowest part of the mixed layer or the atmospheric boundary layer, what we call the surface layer, we use the logarithmic wind profile theory. So what is the logarithmic wind profile? Okay, this is something that maybe you've seen sometime in your past in some course, or essentially implies what I mentioned before, that I drew here is no longer here, was saying that if you have certain flow over a surface, the fact that just at the surface the flow has to be zero implies that the entire flow has to adjust. And that usually generates a profile like this, in which the maximum velocity will occur at a certain height, and then it declines logarithmically down to the ground level, in this case, or the wall, if you're thinking of a pipe, whatever. Okay, so that we call it a logarithmic profile. This is a logarithmic shape. In the case of the atmosphere, the logarithmic wind profile. Okay, and it results from the friction of the surface, right? It's because the surface is essentially exerting friction upon the passing air, and therefore the air has to be zero velocity here, and then it keeps increasing until the top of the surface layer, in which it will just become homogeneous with height, just like humidity and temperature, because horizontal wind, essentially you can equate it with momentum, which also has to be well mixed in the atmosphere boundary layer. So in the mixed layer, above this height, in this case it's just 7 meters, usually it could be more like 20 or 30 meters. Above this height, you have constant wind in the horizontal, you have constant humidity, constant temperature in the mixed layer, kind of. You've seen the simulation. It's not really true. It's in the process of mixing. It's not really well mixed. It's an assumption that we take, and which is the backbone of the mixed layer theory. But down here, this wind velocity has to adjust to the fact that it has a zero value at the surface. So we see this logarithmic profile. So that is caused by the surface friction, right? In case of humidity and temperature, this will look the opposite. And that's why you see right here. In the previous slide, you saw it, right? Kind of like the inverse logarithmic shape. And that has to do, again, with the fact that you're warming and wetting disproportionately here, and that you have the wind being lower here. So it's obviously related because the transfer of heat and moisture occurs through the wind. So if the wind is very low, those will be less well mixed. Yes?
Does the irregularity of the terrain cause the eddies to be smaller, or
causes the
eddies to be smaller?
The values, you said?
It's a mask of
Does the irregularity of the terrain cause the eddies to be smaller?
Yes. So I was going to get to that right now. Yes. So the fact, obviously, that you're closer to the ground implies that the eddies cannot be big, right? It's just a length scale issue. They cannot be bigger. So of course, the closer you get to the ground, the smaller the eddies become, the less effective they become at mixing and so on. So the less energy they contain, if you wish. And that implies that you have essentially a downwards flux of momentum, because you have high wind speed on top, low wind speed in the bottom, and a downwards flux of momentum following that gradient. From the high wind to the low wind, you have a momentum flux pointing down. And that is essentially, in a different way seen, represented by these eddies that are caused by the friction of the surface. So that roughness of the surface causes the wind to actually go down, mix in a way that resembles these eddies. That will be smaller, will have lower energy and lower dissolution power, if you wish, or capacity to transfer as you get closer to the surface, right? So it's a typical profile of wind that you find, and that is actually dependent on a few factors. One of them is the background wind, this U, okay? The strength or the velocity of that wind. But you can see, obviously, something that is quite clear is that from the logarithmic shape, it implies that when you are actually closer to the bottom, the change of wind with height is actually larger than if you separate from the bottom. And you can actually model that change in wind with height if you're interested in knowing what the wind will be at a certain height. And you do it like this. And here I'm introducing two new concepts. One of them is a constant, is the K. It's called von Karman's constant, and it's 0.4. Fair enough. Don't have to worry too much about it. But the second one is important. It's called the friction velocity, or shear stress, we call it as well. And that friction velocity has a very specific definition, which is this one in here. It's kind of like a reference velocity. It's also got units of meters per second, right? And it's defined as the covariance between the wind in the vertical and horizontal. So this fluctuations of wind, this is again the apostrophe means fluctuations, right? Because we forget about the means. We're talking about turbulence. Forget about the means. We're talking about fluctuations of the wind in the vertical and the horizontal, so the covariance of both. That is what we call the friction velocity, and in fact it's the square root of that, because you need to have meters per second, and this is meters per second times meters per second. So you have meters squared per second squared. So in reality, this is the square of the friction velocity, and that's how we define it. All right, so it's kind of like a reference velocity. Reference velocity, which is just the fluctuations in one direction covariant with the opposite direction. All right. That, if you remember what we saw before the break, is actually the flux of momentum. Because we said that the vertical fluctuations of wind with temperature were the flux of sensible heat. The vertical fluctuations of wind with humidity were the latent heat flux. But the vertical fluctuations of wind with wind, or wind times density, is the flux of momentum. Momentum is wind or speed, velocity times mass, or velocity times density. So how that velocity times density changes with the vertical winds is what we call the momentum flux. That is the flux of momentum, all right? So this in fact is the flux of momentum divided by the density, because we don't have the density here. So the flux of momentum would be this times density, as you will see in the next slide. So don't worry about that for the moment. But it's important to keep in mind that this friction velocity is kind of like a reference velocity, and that it will become very useful in the next couple of slides to understand the state of this surface later, okay? So we define it this way: covariance of vertical fluctuations and horizontal fluctuations, or what is the same, the horizontal momentum flux, right? The flux of horizontal momentum, the flux of wind speed in a horizontal times density. Okay, I know this is not completely intuitive, especially when you talk about momentum, it's a lot less intuitive than when you talk about temperature. Okay, so we define this way, but we don't like the fact that we have a derivative here. So we want to actually know what is the wind speed, not the change in wind speed with height, but the wind speed at a certain height. So if we want to know that, we have to integrate, right? So we integrate, and if we integrate this, well, this is a constant, this is a constant, so they come out here. They both come out, and then you end up with the integral of 1 divided by theta, which is an apparent logarithm of theta. And if you are actually integrating between two heights, which is the bottom at which the wind speed is 0, so that simplifies a lot, on the top, then you end up with the logarithm of theta at top minus bottom. And I'll tell you what those are in a second, because it comes across as what did this happen? So you're integrating all of this profile, and the height below is actually not 0, because you want to have the height at which the wind is 0. And that is not just at the interface between the land and the atmosphere, but a little higher. How much higher? It depends on two factors. It depends on whether you have obstacles, trees, buildings, and so on, and it depends on the roughness of the surface. So if the surface is very rough, your height at which the wind is zero will be a little higher. And if you have many obstacles, it will be even higher. So the D here, that we call actually displacement or zero displacement length or zero plane displacement length, which is just in measured in meters, is the height that results from the correction of obstacles, like buildings, trees, whatever. The effect that those buildings, those trees are generating on the wind, that implies that the wind will be zero a little higher. That correction, we call it the zero displacement. All right? And the zeta zero, M, that you see here, is the roughness length. Roughness length is just a correction for the roughness of the surface. So when you correct for both, then you have that the height at which the wind is zero is not zero, but is corrected by the roughness and the zero plane displacement. Okay, the roughness correction is about 10% of the height of the ecosystem, and the zero plane displacement is about 70% of the height of the ecosystem, right? So you end up with kind of like 0.8, so 80% of the height of the ecosystem. If you have different trees, 0.8, that is where the logarithmic wind profile assumes that you have zero horizontal wind, all right? And of course, the higher the height of your trees and so on, the higher that zero wind will be. So the farther up your logarithmic wind profile will start, okay? And that implies that if you're in a forest, there is no horizontal wind, and that is not really true, and you know it. So this logarithmic wind profile theory does not apply to forests. It does not apply to forests within the forest canopy. It applies over the forest. But when you're in the forest, of course, you cannot assume that there is no wind. You know, it's not true. There's still eddies generated by the forest presence. You can have wind in that. This is just not good enough to represent that. In fact, there is nothing good enough to represent the turbulence in a forest. Okay. So we have to correct for the height and start a little higher than the ground level. And we go all the way to the height that we are interested in, that's zeta. So if you wish, you can think of zeta minus this displacement. And the other level would be the roughness length. If you integrate it in between those two levels, you'll get this equation out of this. You can try it later. You can see I'm not lying actually. So that is giving you the height, I mean the wind at any height in the surface layer, all right? That will give you U, that is a horizontal wind, at any zeta, based on essentially a constant, this reference velocity, and a number. This is essentially a number, right? The logarithm. All right. Okay. So that's the logarithmic wind profile, and just keep it on hold because we're going to use it now. I mentioned the momentum flux is pointing down, but the same way, because we have the opposite shape for the humidity and temperature, we have the sensible and the latent heat flux pointing upwards from the higher to the lower. Okay, so those are actually the equations, and I mentioned them before, but I only said it with words. You have the wind fluctuations times the temperature in the sensible heat. You have the wind fluctuations times the humidity being the latent heat, and you have the wind fluctuations with the wind velocity being the momentum force. All right. Now you have also, of course, the density in that, and you have the latent heat of vaporization, and you have the specific, those are kind of like to change the units if you want to think about them simply. Essentially, if you were to have just this, so that's the temperature, potential temperature fluctuations with vertical wind. Then if you multiply times by density, and then you have your specific heat, then you have it in units of energy. And if you want, you can try it I'm absolutely confident because I tried myself. And the same here. If you multiply times the latent heat of vaporization and the density, then you get the latent heat flux in units of energy. If you want to have evaporation instead of latent heat flux, the only thing you need to do is to cross the lambda from both. I didn't do that, but of course the evaporation equals density times the covariance of the vertical wind and the humidity. I didn't do it because I wanted to have both in units of energy, right? So we have the momentum flux pointing downwards from high wind to low wind. We have the humidity and the temperature fluxes, so the latent and sensible heat fluxes pointing upwards from high to low as well. All right, that's how the fluxes move, and they are all driven by this vertical component of wind, this W. What that means is that these are turbulent components, these are turbulent motions that occur through convection. You're not talking about a diffusion through a gradient that occurs through the medium, like the pores, passing water, or the conduction of your fork. We're talking about the moving wind being the transporter for that energy or that humidity. And that's why this is actually expressed as the covariance of that movement of wind with the humidity or with the temperature. The same as when we were talking about the entrainment flux, we were saying it depends on how much energy comes, I mean, how much air it comes and what is the temperature. It's the same. How much air it comes is the vertical wind component, and what temperature fluctuation you have. That is determining the heat flux, right? So the heat moves with the wind because it's a convection process. That's why it looks like this, as a covariance of the wind with the property that you care about. So as latent heat flux, sensible heat flux, and momentum fluxes. And don't want to confuse you, but we saw the Pema-Monteith equation that will come again, like in every lecture at the end. That's a representation of a latent heat flux at the surface level, which considers the moisture at the surface. It considers whether there is water limitation, the resistance of the stomata, and all these things. This is measuring at the atmosphere, the flux, which implies that it has already been diffused into the atmosphere, and now it's just about the wind, whether it moves it up or not, right? So one thing is to actually measure the latent heat flux at the surface. So the interface between the land surface and the atmosphere on top, which is a diffusion. And then another thing is to actually be able to model it in the atmosphere, which is just about whether the wind moves it up. And that's it. So that's essentially what you see here is just merely atmospheric. If you were to have, for instance, soil moisture limitations at the surface, what would occur is that this Q would be smaller. Of course, it has to be consistent with what happens at the surface. So if you have at the surface very little evaporation, then of course this also will be lower. You may have equal wind, but you have less moisture being transported. So your sensible heat flux measured this way or quantified this way at the atmosphere has to be consistent with what is happening below, as long as there is some form of continuity in that, right? So if plants decide not to photosynthesize because there is a beetle killing them, and they don't open the stomata to capture CO2 so they don't transpire because the water doesn't leave the stomata any longer, then there will be less transpiration, there will be less Q in the atmosphere, this term will be lower. Okay, we're just focusing on measuring this at the atmosphere today. We'll get back to the surface. All right, so, and that's actually what I'm mentioning here, that there is nothing in here about radiation, because we are not looking at the land surface partition of radiation. We're not talking about albedo, etc. There is nothing about water limitations because it's just merely atmospheric. We start from the point in which you have humidity already in the air. We don't care how it got evaporated, and then we are seeing how much is being moved up through the vertical winds, right? It's a convective process, okay? So that is the basis of the eddy covariance techniques. I'm not sure if you saw today, I saw in the faculty news, first eddy covariance tower constructed in the Congo, which is true, is my colleague Pascal books. And it's So that eddy covariance technique is what we use to measure fluxes of water, CO2. We can also measure temperature, heat fluxes, and so on. So eddy covariance, if you haven't seen it yet in any lecture, you'll see it with Nico. He'll probably show you some instruments. Have you actually already got some eddy covariance? You'll see it. You'll see, he'll show you the instruments and so on at some point. But you use the eddy covariance technique to measure carbon fluxes, for instance, photosynthesis, respiration. You use it to measure evaporation, latent heat flux, sensible heat flux, and so on. So anything that is moved through the winds in the atmosphere. Through convection, you can measure any pollutant, flux, and so on. For that, you use this eddy covariance technique. And it's called eddy covariance because it's measured, it's based on the covariance of the variable that you care and the vertical wind, the eddy, right? It's based on this, and it measures that. That's exactly what it measures. It measures with two instruments, one that is measuring the variable, the thermometer, if you're measuring a heat flux, or it could be a vapor analyzer, or it could be the same for CO2, something that measures the concentration of CO2, and another one that measures the wind. So it's two instruments. And the one that is measuring the wind is calculating the W apostrophe, and the other one is calculating the property that you care. It could be humidity, it could be temperature, and that way you work out the fluxes this way. And that's the only way in which you can actually accurately measure evaporation in nature, or you can measure sensible heat or photosynthesis and transpiration for an ecosystem. That's this eddy covariance technique. And you'll see it later in other lectures, and that's why I put it in there. It's based on this, essentially this, the covariance of the vertical wind with the property that you want to diagnose, all right? So it measures fluxes, carbon, heat, moisture. All right. Any questions before things get a little harder? Okay. Now, let's go back to diffusion and conduction, just for a second, because I want to draw an analog. How is the conduction happening? Well, it happens again because you have a gradient in temperature and you have certain conductance, and it just travels. The flux travels from the high values to the low values of temperature, right? That's for conduction. But it's the same way that the Ohm's law works for electricity, the same way that the Darcy law works, Fourier law, and the Fick's law for diffusion. In physics, there are many, many different laws that describe fluxes that way, which is the gradient and then some conductivity, or divided by some resistivity, which is the same. Conductivity and resistivity, they are inverse. So you usually, if you think of conduction, you have two, for instance, if I take this and this is 100 degrees, I'll feel eventually the heat here, if this is super hot, when it actually travels through conduction across my arm, and the velocity of that flux would be, or the flux would be actually proportional to the gradient in temperature between this and my elbow, and my shoulder, sorry, and the conductivity of my arm. So essentially it implies that you're not moving the heat with the medium, but you're just actually transporting it through the medium because of gradients, in this case in temperature. Same, as I say, works for many other properties like electricity and so on. Okay, so if you want to represent that mathematically, it's just this. You have your sensible heat flux, which is proportional to the temperature. There's potential temperature change of a certain distance multiplied times a conductivity, right? And this, as I said, just forget about it, kind of like a unit conversion. It makes sense if you think about it, but let's say that you want to have energy units here, so you have to convert it. Okay, that is called the Fourier's law. That's how you actually estimate conduction, all right? If you want to have the equivalent for moisture transport, so the diffusion, then you have this formulation, which is called the Fick's law. Okay? Fair enough. But we said that that is not really how it works in the atmosphere, because you don't have conduction and diffusion, but you have actually the movement of the of the humidity and the temperature transport occurring through convection. So there was, back in the 19th century, French scientist, this guy Business, that decided to introduce what we call now the eddy diffusivity or eddy viscosity in the case of momentum, which is equivalent to this constant here, this conductivity or diffusivity that you have here, but it'll have a different number. So essentially, he's implying that you can also calculate convective processes as a gradient. It's just that the conductivity is going to be larger because you have more means to actually efficiently mix and so on, right? So the process will be more efficient. So that conductivity that you have in here that takes a different name will actually be larger than the one that you can use for conduction and diffusion. But you can represent convective processes in a way that is one-to-one analogous to how you represent diffusion and convection. So that's what this guy tried to do. He called that, as I say, eddy viscosity or eddy diffusivity for the constant. Actually, he didn't because he was French, but he called it something similar. The word eddy actually didn't come until Reynolds, about 50 years later. But yeah, then it got to eventually be known as eddy diffusivity. So this has one advantage, is that if we want to compute the fluxes, because here we were measuring with the eddy covariance. You have a tower, you can measure the fluctuations of wind, you can measure your temperature and humidity, and then you have the fluxes. But how many of those we have? We have about 300 in the entire world. So if you want to know the evaporation here, if you want to know the sensible heat, the photosynthesis, respiration, we don't have the means to actually compute it this way. So we try to estimate it. How do we estimate this? One way is to assume it's a diffusion. We will fail because it's a lot more efficient than a diffusion. You need to have constants here that are a lot higher. So then you can try this with different constants, different conductivities. That is what this guy actually proposed. Problem, you still have those conductivities there that you don't know. I have no idea what this is. But you can assume one thing is that it's the same for heat, for moisture, and for momentum, because they are being moved by the same mass of air. Since they are being transported by the vertical winds, we can assume that the conductivity is the same for the sensible heat, for the latent heat, and for the momentum flux. And if we do that, you can calculate the ratio, for instance, the sensible heat to the momentum flux or the latent heat to the momentum flux, it doesn't matter, and these two go because they are the same. You're assuming they are the same, right? And if you do that, you have a formulation to calculate evaporation that is not too horrible. And that is telling you that the evaporation is somehow proportional to the humidity at two heights and the wind speed at those two heights. So if you measure humidity and wind at two heights, you don't need to have these super complex eddy covariance systems. You can actually estimate evaporation. The problem is that you still have here this momentum flux. And that is actually something that you don't want to have because you have no idea what it is and how to measure it. So how do we get rid of that momentum flux? First thing that we know is the definition of the friction velocity that we saw before with the logarithmic wind profile. Okay, that is this. It's just the square root of the momentum flux over the density. Okay, keep that in mind. Now we have the logarithmic wind profile equation, the shape of the curve, which is nothing but the u, so the speed change with zeta. Okay, that's the logarithmic wind profile equation, right? So you have the logarithmic wind profile equation. You have the definition of the friction velocity, and now let's see if we can get rid of this tau from here. So the first thing we do is to convert this in something a bit more like this up here. So you're just thinking about two heights. instead of the humidity, the wind speed at two different heights, the wind speed between two heights. All right? To have it similar to how you have it in here. And if you do it, you just have this at one height, which is 1 minus height 2, or the other way around, it doesn't matter. You get this equation here. Likewise, you can clear up this equation and put the momentum on the left. So that's essentially the momentum flux based on this, on the friction velocity. Next step, you isolate your friction velocity here. So you end up with this formulation. And if you do that, I don't want it to look like magic, and that's why I'm going through these steps, because I'm not pretending you to actually understand the steps mathematically until you have a better look at it, but it's better if I don't give you just the equation. If you do that, then you can replace the U star, the friction velocity, in this equation, and you get this, all right? Now, this is your tau, the tau that you need here. So if you replace your tau formulation in this formula, then what you end up with, 2 steps if you want, is this in here. Now, this in here doesn't have the tau at all. This in here is just humidity and wind speed at 2 different heights. That implies that if you have the means to measure wind speed, horizontal wind, you don't need to have high resolution vertical motions or anything like that, just normal wind speed at 2 different heights and the humidity content at those 2 heights. Knowing those 2 heights, of course, you can calculate evaporation. If instead of putting here evaporation or latent heat flux, you put the sensible heat flux, you can do the same and calculate the sensible heat flux here. The only thing that will change is that instead of having humidity, you need to have temperature here. So if you measure temperature at 2 heights, you know the heights, and you know the horizontal wind, you know the transfer in the vertical between the 2, and that is based on the logic behind the logarithmic wind profile. So essentially, knowing the vertical motion, knowing the horizontal motion of the wind and the temperature at 2 heights, you get to know the turbulent flux in the vertical, right? And that is something that is quite useful. It's called the Thornton-Waite-Holtzman equation. And they use it quite a lot in engineering. I personally, in research, don't use that. But if you encounter it in the future, it would be good that you remember that it allows you to measure or to estimate evaporation from the atmosphere at 2 different heights. Also allows you to calculate latent heat flux. It would even allow you to calculate fluxes of CO2 and so on if you replace it properly. And it's all based on the rationale of this logarithmic wind profile, because you actually used it in here, and because you use the definition of friction velocity as well to get rid of the momentum flux up here, right? So, any question? I know this is not immediately intuitive. It's the kind of things that you have to probably sit down and actually try to grasp it on your own. But if there are things that you didn't understand at all, we can certainly review them here. So one thing I did mention already is that in forests, this is not going to work, and you can see why. If you look at the red, it could be kind of like a real wind speed profile. It's not at all logarithmic like we are proposing, actually. The black will be the result of the logarithmic wind profile theory, corrected by the displacement law, the displacement length, and also by the roughness length. And you see that in reality, that will predict that in this case, below 8 meters, you don't have any winds. While we know that in reality, we do have winds within the forests. And therefore, the theory doesn't really work in the case of forests. So you cannot use, for instance, this equation that we just saw, the Thornton-Waite-Holtzman equation within the forest canopies in the middle of the forest. You can do it over the forest, but you cannot do it at 2 heights within the forest because the logarithmic wind profile doesn't apply within the forests. Okay. Now, things are just going to get slightly worse, but not too much. Okay? The logarithmic wind profile is based on neutral atmospheric conditions. We are assuming the atmosphere is neutral, meaning that it's not stable, it's not unstable, all right? It just has a perfect one-to-one match between the dry adiabatic lapse rate and the environmental rate. So we just have a perfect adiabatic lapse rate, dry adiabatic lapse rate in the atmosphere, meaning that it's a neutral atmosphere. And that's the only case in which the logarithmic wind profile works out of the box. If you have either a stable or unstable situation, that change in wind with height is going to change. It's not going to be the same. And we need to correct it. And that's what these guys, Monin and Obukov, back at the end of the previous century, did with this similarity theory. They worked out a way to correct the profile of wind for any stability condition so that we could know what is the height or what is the wind at a certain height independently of what is the stability of the atmosphere. And as you have seen, that allows you to calculate the fluxes, not just of momentum, but also of sensible and latent heat, as long as you can actually correct that logarithmic wind profile for stability. So how did they correct the logarithmic profile for stability? They made up this unitless correction, which comes out of this curve. Now, take a deep breath, try to understand what I'm going to say now, because as I said before, it's not the most intuitive thing. Now, you have here a function of something. That something is what you have here in the x-axis is a length. That is also unitless because it's the height divided by this L that I haven't explained yet what it is. That is the key in this correction. So you have this in the x-axis that if you calculate it, you can work out what is your correction that you need to use, all right? So if you were to be able to calculate this, and I'll show you how you calculate it, the x, then you can use this shape of this curve that is universal, magically, to compute what is the correction that you need to put in here for stability, okay? So what is that x-axis? That x-axis is just as it says in the axis, the height divided by the Obukov length, L. The height here, I actually corrected it by the displacement plane. You don't need to do that, not necessarily, but well, that's what you call theta. Of course, if you call theta the height, or you call theta the height already corrected by the displacement height, that makes it sometimes a little confusing when you read different books and so on. But here you can see the axis is not corrected. Here I did correct it, doesn't matter. So you have to essentially divide your height, which you care about, over this Obukov length, which is this in here. I'm not going to go through what is the formulation of the derivation of that, but I want to point out to one thing, is that you have in here the sensible heat flux. As the sensible heat flux takes the V because it's actually calculated not with temperatures, but with virtual potential temperature. That's fine. I mean, it's not going to change too much because you're looking at two levels that probably have similar pressure. And you're looking at levels that probably have similar humidity content. So that correction is not that much needed. But think of virtual potential temperature instead of temperature. Well, that is this sensible heat flux here. Okay, HV. What that means is that if your sensible heat flux is high, this equation is going to be negative, right? You're going to have a negative here, this L. So this will be negative. So you're here in this side, in the negative side, which implies that the correction you have to apply is positive. If you remove a positive number here, the wind is going to be smaller, right? You're making this entire thing smaller, the wind is going to be smaller. So when you have high sensible heat flux, the wind will be smaller in a horizontal. When do you have high sensible heat flux? When you have instability, unstable conditions. You have sensible heat flux coming, warming the atmosphere, and the atmosphere, the air has been warmed up and moves up. That would imply that your profile of wind is less steep, so it grows less with height. So there you have it. You have unstable conditions. You will have this being positive and large, so you will have warming of the air from the surface. Or if you want to think, if you don't want to think about the surface to the top of the air, maybe you want to think about 2 layers of atmosphere. That might be easier. You have 2 layers of atmosphere. You have a sensible heat flux that goes like this, which is positive for convention. We call a positive flux is actually flux from the surface up. Negative is the other way around. Probably should have mentioned that. So when you have H being positive, meaning that it goes up, you have unstable conditions, right? You have an upward movement of high temperature air, you have unstable conditions. So when this goes up, this is positive, unstable conditions. This will result actually in a positive here, which will lead to lower wind with height. So you end up with a profile that looks like this, meaning that horizontal wind increases less with altitude than if you were to have stable conditions. And that, if you think about it, is actually not that counterintuitive. If you have a certain flow in a horizontal and you're being warm, or that you're warming that flow from below, it's going to slow it down in the horizontal and increase the vertical component. You want to maintain the flux of momentum. So essentially, you have your horizontal wind, and as it is unstable, so it's tending to move in the vertical, then the final increase in horizontal wind with height will be lower than if you had a perfectly stable condition in which you have no vertical motion distorting that horizontal flux. So if the horizontal flux is not being distorted by the vertical motion, then it increases faster with height than if it is. And in reality, when you look at that, it's a little misleading, because I said before that on top of the surface layer, you need to have no effect of the surface by friction. So eventually it comes to a point in which the horizontal wind is the same, independently of what the surface is doing, which is the top of the surface layer. In the mixed layer wind is no longer affected by the roughness in that sense. So in reality, it doesn't look really like that, because it has to come up to a point in which they agree. So it really looks, well, certainly not like that, like this. The only thing is that you're seeing just this part of the figure, right? But eventually, at the end of the surface layer, they will agree with each other. So it's just about the speed in which it increases with height, or the rate at which the wind increases with height, what is changing. But eventually, you'll get to the same level, which is the level that the wind, horizontal wind, has without friction on the surface. Right? Over here. Okay. Now, I took this out because I didn't want to confuse you more, but you can actually use just keep in mind that you can use the logarithmic wind profile with this Monin-Abu curve similarity corrections for unstable and stable conditions, not just to calculate the wind changes with height, but the humidity changes with height, the temperature changes with height, and as you saw before, the fluxes. So in reality, to represent the state variables of the surface layer and the fluxes within the surface layer, you can use the logarithmic mean profile in combination with this if you need to have stable or unstable corrections. All right, and that way you'll know the changes in height of humidity, temperature, and wind speed, as well as the latent, sensible, and momentum fluxes. Okay, so you can also use this to calculate what I was saying before was not well captured by the mixed layer, which is this profile layer, the change in humidity and temperature with height within the surface layer, right? And I didn't show you how to calculate it because I thought it was a bit too much. It's in the supplementary, you don't need to know it, but if you're curious, the only thing you need to know is that anytime you see wind, you can replace it for humidity or potential temperature, and it will still work out. Instead of doing a momentum flux, you will be doing a heat, sensible heat or latent heat flux. The advantage of looking at wind is that we know it's zero at the level zero, and that's why this equation looks a little simpler, because otherwise you will have humidity at level theta minus, wind at level theta minus wind at level zero. The fact that wind at level zero is zero simplifies this. If you had actually potential temperature at level theta, you have here minus potential temperature at level zero. And then the equation here will look pretty much the same. It's just that the friction velocity, instead of calling friction velocity U star, you have Q star or theta star, which is just equivalent in the way you define it, but for the heat fluxes or the, yeah. So as I said, I took it out because I thought it was too much, but it's important to keep in mind that for the surface layer, if you have both the theory behind the logarithmic wind profile and the corrections from Moni Nobuko for the stability, you can represent the changes in humidity, temperature, even CO2 in the first few tens of meters of the atmosphere, as well as the fluxes, which, as you have seen, are actually constant because changes like that. It actually is mentioned already there. So, any question at this stage? We just have one more thing to see today. And I promise you that the following lectures are going to be a bit more intuitive. Turbulence is not the easiest thing to grasp, especially not on first sight. But if you have questions now, it's good to ask them because quite certainly a lot of your colleagues also have similar questions, if not the same actually. So don't hesitate to do it. Yes?
You explain the L again. So when the sense influx is becomes bigger, the L is always negative. Or so what has sense the point barrier and then
yeah, so if this is negative, so imagine, yeah, if it becomes bigger and positive, this is going to be positive. That the opposite situation would be to have actually a negative sensible heat flux. Very stable conditions like what you have at night, in which you have actually the heat flux pointing down because you have very cold air below, or the surface is very cold, and on top is actually warmer. So the heat flux goes the opposite direction, and actually you have very little convection. So most of it in that case will be through conduction, and it's not much, right? In a stable situation like that, what you have is a negative sensible heat flux. So that negative will be cancelled with this one. So you have a positive length, which will imply a positive buoyancy parameter. So if you replace it here, you're in this side of the graph. So you would end up with a negative correction here. Negative and negative means positive. So this number is going to be higher. So you're going to have a higher wind with height when you have a stable situation like that with a negative sensible heat flux. Yeah. Okay. Again, our favorite equation. So we have pretty much everything that we need now in the Pemberton-Monteith equation to understand it and to derive it. The thing that we need to actually get our heads around today is this RA, which is the aerodynamic resistance. And everything that we have done up to this point was needed for you to actually understand what we are going to do next. To calculate this aerodynamic resistance and to know what it actually means, the aerodynamic resistance, right? So, as I mentioned before, this equation is very important to understand. The heat fluxes from the surface into the atmosphere, therefore the influence of the atmosphere on the surface, but also the influence of the surface on the atmosphere. What would happen if we have deforestation to the hydrological cycle or to temperature, things like that. You use it to measure or to quantify the needs for irrigation. You can actually use it for many things. So it's actually the most important equation in this course. Most of the terms are in here. We already saw them the last week, actually. But this RA has been somehow elusive. So let's see what it is. So that RA, which I mentioned, is the aerodynamic resistance. Sometimes I will refer to it as aerodynamic conductance, which is the inverse, right? Just 1 divided by the resistance. It takes units of meters per second, fair enough. Don't think about it as a velocity, but maybe it helps you, like the ability to move the air. But that's essentially what it is. It really gives you a diagnostic of whether the atmosphere is capable of convecting the heat or the chemicals or whatever. It's kind of like that conductivity that we mentioned before. Very similar to that conductivity. So when we said the conductivity but for convection, and we introduced this guy, the French guy, Miralles, saying, hey, maybe we can do like for the diffusion and conduction, but have a constant that is actually for convection, which is actually higher because it implies that we have a medium that is more capable of effectively mixing and transporting. This conductance, aerodynamic conductance, is exactly that. It has slightly different units because you're not looking at the conductivity per meter. You're not looking at the gradient, but you're just looking at the conductivity. So you have 1 less meter, as you'll see, that you had in the K from Miralles. But it's the same concept because the Miralles K, that conductivity that Miralles introduced, that he called eddy diffusivity, was actually the gradient, as the difference between, for instance, temperature in 2 points over the distance between the 2 points. This is, imagine no distance in the case of the aerodynamic conductance, because you're looking at the surface and then the layer of atmosphere on top. So it's really just the difference in temperature. So while the other one was the difference in temperature over the distance times a constant, is constant, this is just the difference in temperature times a constant. Not over the difference, the distance. And that's why the units are a little different. Otherwise, it would be just exactly the same physical variable. So one is just in space, and this one is more like immediate, like between 2 layers in contact, if you wish to think about it like that. It doesn't have that gradient nature, it's just a difference between 2, and then how you would actually effectively transport between them. So what it is just conceptually the same. It's just the ability of the atmosphere to transport and to conduct or to convect. It's just a higher when you have the atmosphere with higher winds and more capable of moving the air, and it will be lower when you have very stable and very steady atmospheres. It will be higher when you have, for instance, vegetation introducing roughness, creating eddies, and it will be lower when you have a very bare surface in which you don't have a lot of motion. So that is essentially what the conductance is. And the resistance, the opposite. The aerodynamic resistance will be higher when the atmosphere is less prone to transfer. It has a higher resistance to the convection and to the transport of heat, moisture, whatever. Okay, and if you were to simplify this Pena-Montis equation to something very, very basic, which is equivalent to actually what you saw before with the Fick's diffusion and the Fourier conduction formulas, but in this case, we are just actually making it a bit more realistic because we're thinking about the land surface and the atmosphere on top. we can actually represent the latent heat and the sensible heat flux this way, which is just essentially the same as I just mentioned, which is the gradient between the humidity at the surface and the humidity in the atmosphere right on top, divided by the resistance or multiplied by the conductance. It's the same. But here you have an extra resistance, which is your surface resistance or stomata resistance for transpiration, right? And that is in here, in the Pema-Montijo equation, but we haven't seen it yet. I know that you've probably seen something with Kathy, but it's essentially a function of soil moisture and so on. So the degree to which your surface wants to conduct the vapor outside, which is a function of whether stomata are open, in the bare soil, whether you have enough soil moisture or critical soil moisture, and so on. But that is this RS that you have to account for when you're actually thinking of evaporation, but you don't need for the case of sensible heat flux. The sensible heat flux, the surface is not actually containing the flux at all. There is no stomata closing to escape, to prevent the escape of temperature. For water vapor, yes, but for temperature, no. So that's why this formula for sensible heat flux at the surface doesn't have that resistance from the surface. It just has the aerodynamic resistance, which is pretty much the same as for vapor. Those two are pretty much the same. The aerodynamic resistance for vapor and for the heat temperature is the same because they are both moving through the same mixing air. It's all moving out through convection at the end, right? So this equation is just equivalent to that one that I showed you for Businesque, but with this conductance instead of his diffusivity, which, as we said, have slightly different units because they don't have the surface gradient in between two points, but actually it's just the difference between the 2 points. In this case, you see the points, atmosphere and surface divided by the resistance or multiplied times the conductance. It's the same. Okay, so if we start with this, which would be a good endpoint, but then this guy actually decided it was not good enough, and a few others. And the reason it's not good enough to calculate evaporation or to calculate sensible heat flux is that it's super difficult to measure the humidity at the leaves level or in the pores and humidity vapor, and then right on top is a mess. So you can never actually go to the field and measure what you need to actually work out the fluxes this way. That's why this is actually, even though it works, it's a lot more practical and a lot more accurate. But if we were to start from very, very bare physics, which will be this, you have a gradient in humidity and certain resistance, and you have a gradient in temperature and certain resistance, that will be the formula that you will need, and that resistance will be your aerodynamic resistance. So essentially the capacity or the willingness of the air to conduct and convect that, right? Okay, so if we look at those two equations, we're going to work out the way to calculate the aerodynamic conductance. Yeah, go ahead.
A question about previous one. How does the aerodynamic conductance explain the interception loss in the forest?
Yeah, we haven't got to that yet in the course, and actually, I probably shouldn't have mentioned this in here, but the aerodynamic conductance in forests is going to be high, and it's higher despite what the logarithmic wind profile says, that it tells you that at the same height in a forest, the wind will be lower, right? In reality, what happens is that you have the winds coming and then the trees are actually blocking it and they are creating eddies and they generate a very turbulent atmosphere that is very conductive. So what happens is that in interception loss, since you're putting that water on top of the leaves where there is already some wind, we're not at the surface any longer, and there is eddies in the forest and so on, what happens is that that air is super conductive. So the moisture that stays there has a very high aerodynamic conductance and it gets evaporated very quickly. Okay? So that's the reason why the interception loss is super powerful. If you measure the rates of interception loss or how much interception loss you have per minute, it will be more than transpiration. And that's because the water on top of the leaves is exposed to this passing air that is super dynamic and squarely and effective at transporting that. So the aerodynamic conductance in forests is very high. The resistance is very low, and that causes the interception loss in forests to be very, very high. Okay. So this is the same equation. I didn't do any magic. The only thing that I did was using the conductance instead of the resistance, all right? And I added also the momentum flux, which is the same, but for the wind speed, all right? Instead of humidity, instead of temperature, we have wind speed here. Now, why is that actually convenient? Because we know that the wind speed at level 0 is 0, right? We mentioned that before. So then the momentum flux takes this form that is not very difficult, actually. You just have wind at the atmosphere, and then you have the conductance of the atmosphere and the density. That's kind of like an unit conversion, if you wish. So if we assume that the conductance is the same for heat and moisture and momentum, then we can actually do something that is quite convenient, which is to define the conductance based on the momentum flux, which is simpler because you don't have momentum at the surface level, right? So if you actually do that, so you take this equation and you work out what the G is, you use the concept of the friction velocity here. You know that the momentum flux equals this from the previous slides. You end up with this in here. So your conductance is just the friction velocity squared divided by the wind speed. We don't like it yet because it's still not very easy to apply. So if we now evoke the logarithmic wind profile, and that's why I said, well, to understand the aerodynamic conductance and what it is and how to formulate it, we need the previous slides. We need to know what the aerodynamic, what the logarithmic wind profile is and so on. So if you actually use the logarithmic wind profile here and you replace your U, in this case, or your U star, actually your friction velocity, you end up with this equation that you see here that is called the Ton's equation, and is the normal formulation for aerodynamic conductance. So if you were to actually apply in the future the Pema-Monteith equation, the equation requires that aerodynamic conductance or resistance, which is inverse, which is calculated like this. And you can see here again the morning of the Prof coming for the correction of the stability, and you can see essentially the logarithmic wind profile in there. Okay, so that is the normal formulation for aerodynamic conductance. And what I mentioned before, actually, forests being actually very aerodynamic conductant implies that the sensible and latent heat flux will tend to be larger. So that is one of the factors why the latent and sensible heat flux will tend to be larger over forests. You saw in the video of the Amazon in the first lecture, all those clouds forming on top of the atmosphere. In the Amazon, we said that is because they transpire a lot. But why do they transpire a lot? They transpire a lot because they have deep roots, because they are opening the stomata a lot, but also because the wind is actually moving that up. So we have to think of surface resistance, so whether the stomata open or not, and whether there is water in the ground, but also the aerodynamic resistance, whether actually that air will be then moved up. Because what happens if you don't have aerodynamic conductance? So if you don't have the air moving up, that the air on top of the vegetation will saturate. And if the air saturates, when the stomata open to capture CO2, they don't lose water because there is no gradient between the surface and the atmosphere of water vapor. But for the plant, that's great because it doesn't want to lose water. But of course, it implies that the transpiration will be a lot lower. So the aerodynamic resistance or aerodynamic conductance is still modulating the rates at which plants lose water through transpiration, or soils lose water through direct evaporation of water. And also, of course, modulating the sensible heat flux. If you have no aerodynamic conductance, the layer on top of vegetation will warm up, it'll stay warm, there will be no more gradient between the plant and the air on top, so it will suppress the sensible heat flux, normal sensible heat flux. If you have the wind moving out that warm air, then of course you will keep on having cold air coming, and that heat flux will keep fueling. And that will determine, for instance, whether forests can warm or can cool down the environment. It will determine whether they are positive when you have a heat wave, or they are actually bad for you when you have a heat wave, and so on. So in reality, this aerodynamic conductance is tendency of the atmosphere to mix and transport heat and moisture, but also CO2, for instance, will be crucial to understand the influence of the land surface on climate. If you think, for instance, another case, I mean, this is the beauty here is that anything that happens in the surface layer and the atmospheric boundary layer is covariant. That's why the covariance. So if you have the heat fluxes and moisture fluxes covariant, you can also think of the CO2 fluxes covariant. If you were to have actually no vertical winds, no aerodynamic conductance, and the plants start to photosynthesize, what's going to happen? That they are going to deplete the CO2 that is right on top of them. And when they open the stomata, they won't be able to diffuse inside any CO2 because the released CO2 is zero concentration. They just consumed it through photosynthesis. So they open the CO2, they want to have a positive gradient so that the CO2 gets diffused inside. But if the CO2 has already been consumed on top of the leaf, then of course there will be nothing being diffused inside. And unless there is wind actually and aerodynamic conductance replenishing that and renewing the air on top of the leaves, then the photosynthesis will be shut down because the plant will be unable to capture CO2 as it's being depleted right on top of it. If you have, for instance, a very, very shallow atmospheric boundary layer, in which you have a day in which the H is very, very low, so there is no warming of the land surface, there is no growth of the atmospheric boundary layer, your container is very shallow, photosynthesis consuming CO2 is going to deplete the CO2 concentration in that container. If that boundary layer was actually deeper, because there is more convection, that is going to contain much more CO2 for the plants to be able to use in photosynthesis, especially if that is actually also being renewed. So it's not just about moisture, it's not just about heat, it's also chemicals, it's also carbon, methane, CO2, photosynthesis, respiration. All these things are connected, and in the atmosphere, they covary because they're transported by the same momentum flux and the same winds. And that's why it's important to understand how the wind dynamics actually work, because they can help you understand these fluxes of different chemicals and energy. Okay? We're getting there. So, aerodynamic conductance is higher when you have high winds, unstable atmosphere, tall vegetation. High winds, unstable atmosphere, short vegetation. High winds, stable atmosphere and tall vegetation, and the one that I haven't said. Or it's low wind and chaos in the universe. So let's start from the bottom. Does anybody think that it's actually higher when you have low winds, the aerodynamic conductance? No, right? Good. Option B. Option C. Yeah. Some hands there. Option B. And option A. Okay, so it's between A and C. And let me see what the difference is. Stable or unstable atmosphere. Okay, that was a little deceiving. You can work it out and see that it actually is a little higher when you have unstable atmosphere. And that has to do with the vertical motion. If you apply this equation, you will realize that that is the case. The thing is, it comes across as difficult to see from the equation because you have the correction here, and you have the wind there. Trust me on A is the right answer. But it also depends on the scale. And I'm gonna tell you why very briefly. If you were to have a very stratified atmosphere, like the ones that I just mentioned, in which you don't have vertical mixing with the top, what you would actually have is that all the wind would go in the horizontal, and the air, let's say, that comes from there that has already been wet and moistened and warmed up and depleted from CO2 there will come in here. So that will imply that that air is not capable of actually transporting as much as if it was actually mixed with the top layers that have not been depleted of CO2, that they are still colored and they're still dry. So that capacity of transport is not just only about winds, it's also about the ability to actually conduct the heat and moisture. I have to actually think about this answer a bit more, but and I should have, but I think we can take my word for granted. When you have unstable situations in general, the conductance is actually high. And if you go to the formula here that we had for the wind correction, we said here that if you have unstable atmosphere, so you have an atmosphere that is like this correction will be positive, right? So this number will be positive. So this entire thing will be smaller. So your wind with height will be smaller, right? So this number becomes positive when you have unstable conditions. But in the formula of the aerodynamic conductance, that is actually to the power of -2. So it has kind of like the opposite effect on the conductance, right? So you see here, actually, when you have a positive number here, this entire number will become smaller. So this is actually to the power of -2. So you're making the conductance high. Okay. Actually, you have here, this is actually just for the canopy height, but the difference is in canopy height and how they affect conductance. So if you have a very high trees here, you have a higher conductance. Okay, so I'm not going to go through this today because it's a little late, but we'll revise all this in the next lecture. But you see that we have gone all the way from the mixed layer theory and boundary layer to the logarithmic wind profile and then the conductance. And I think that that was a lot of information. As I say, we will revise this in the next lecture. And if there is any question now, I'll be happy to take it. And otherwise, I wish you a great week. And anything that comes out to you when you're reading the material or whatever, just drop an email or come to my office. Maybe drop an email because these days I'm not very frequently in the office, and I'll most likely reply